Welcome back. Tonight, we settle in with the gentle hum of distant telemetry as we follow a spacecraft that drifted for 7 years through the cold black, past Jupiter's swirling storms, before slipping into the golden embrace of Saturn's rings, where it would spend 2 quiet decades photographing hexagonal polar storms, icy moons hiding subsurface oceans, and the methane lakes of Titan, all while sending home whispers of data across 1 billion miles of silence. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. The story of how a spacecraft comes to be as often as quiet and methodical as the long years it will eventually spend traveling through the darkness between worlds. And so it was with the Cassini-Huygens mission, whose origins can be traced back to a time when Saturn was still largely a mystery wrapped in golden bands of cloud and encircled by rings that no human-made object had yet studied in any sustained way. The dream began to take its earliest recognizable shape in 1982, when scientists on both sides of the Atlantic began to consider what might be possible if their respective space agencies were to pool their resources, their expertise, and their shared curiosity about the outer solar system. In that year, the European Science Foundation and the National Academy of Sciences in the United States each put forward proposals for a joint mission to Saturn, recognizing that the scientific questions surrounding the ring planet and its many moons were too vast and too compelling to be addressed by any single nation working alone. These early proposals were modest documents in a sense, careful outlines of what might be achieved, and yet they contained within them the seeds of what would eventually become one of the most ambitious planetary exploration missions ever undertaken. The scientists and engineers who drafted those early concepts understood that a mission to Saturn would require patience measured not in months but in decades, for the outer solar system is impossibly far by any human standard, and the planning alone would consume years before any metal was bent or any circuit was soldered. They envisioned an orbiter that could circle Saturn for an extended period, studying the planet and its environment in ways that the brief flybys of the Pioneer and Voyager spacecraft had never been able to accomplish, and they imagined a probe that could descend through the thick orange atmosphere of Titan, Saturn's largest moon, which had tantalized scientists ever since they had discovered that it possessed a dense nitrogen-rich atmosphere not entirely unlike the atmosphere that may have surrounded the early Earth. These twin goals, an orbiter and a landing probe, would define the mission's architecture from that point forward, and the collaboration between American and European scientists would prove to be one of the defining features of the entire endeavor. When it came time to name this ambitious undertaking, the scientists looked backward through the centuries to honor 2 astronomers whose observations had first revealed the wonders that the mission would seek to explore in such detail. Giovanni Domenico Cassini was an Italian-born astronomer who spent much of his career in France, working at the Paris Observatory in the service of King Louis XIV, and it was Cassini who, in 1675, discovered the dark gap in Saturn's rings that still bears his name, the Cassini division, a space between the bright A ring and the B ring that would eventually be revealed as a complex region shaped by the gravitational influences of Saturn's moons. Cassini also discovered 4 of Saturn's moons during his years of careful observation, adding to humanity's understanding of the Saturnian system one patient night at a time. The probe that would descend to Titan was named for Christian Huygens, a Dutch mathematician, physicist, and astronomer who, in 1655, became the first person to identify Titan as a moon of Saturn, using a telescope of his own design to peer across the vast distance and recognize that faint point of light for what it truly was. Huygens was a polymath of remarkable breadth, contributing to fields ranging from probability theory to the study of light. And his discovery of Titan opened the door to centuries of wonder about what that distant moon might be like. To name the mission after these two pioneers was to acknowledge that all scientific exploration stands upon the foundations built by those who came before, and that the instruments traveling to Saturn would be, in a sense, extensions of the same human curiosity that had driven Cassini and Huygens to turn their telescopes toward the night sky so many generations earlier. The formal approval of the Cassini-Huygens mission came in 1989. When both NASA and the European Space Agency committed to moving forward with the project, agreeing to a division of responsibilities that would see the Americans build and operate the main orbiter, while the Europeans constructed the Titan probe. This approval was a moment of quiet celebration for the scientists who had worked for years to bring the mission to this point, but they soon discovered that approval was not the same as certainty. For the years that followed would bring challenges that threatened to end the mission before it had truly begun. In the early 1990s, the United States found itself grappling with budget pressures and shifting political priorities, and large-scale science missions became targets for those who sought to reduce government spending. Between 1992 and 1994, the Cassini mission faced cancellation not once but twice, as members of Congress questioned whether such an expensive undertaking could be justified in a time of fiscal constraint. The debates were contentious, and the outcome was far from certain, with the mission's fate hanging in a delicate balance that shifted from one budget cycle to the next. During this period, NASA itself was undergoing a profound transformation under the leadership of Daniel Goldin, who had been appointed as the agency's administrator in 1992 and who brought with him a philosophy of doing more with less, captured in the phrase faster, better, cheaper. Goldin pushed NASA to embrace smaller, more frequent missions rather than the large flagship projects that had defined planetary exploration in previous decades, and the Cassini mission, with its enormous scope and substantial price tag, might have seemed an obvious candidate for elimination under this new approach. Yet the mission survived, in part because the international partnerships that had been forged made cancellation diplomatically complicated, and in part because the scientific community rallied to defend the mission's unique value. The European Space Agency had already invested considerable resources in the Huygens probe, and walking away from Cassini would have damaged the trust that undergirded transatlantic cooperation in space exploration. The Italian Space Agency, known by its acronym ACI, had similarly committed to providing critical hardware for the mission, and these international entanglements created a web of obligations that helped to sustain the project through its most vulnerable years. By the mid-1990s, the political battles had been won, at least for the moment, and the mission was allowed to proceed toward its launch. The partnership that built Cassini-Huygens was truly international in scope, drawing upon the talents and resources of 17 countries across 3 continents. NASA's Jet Propulsion Laboratory in Pasadena, California, served as the managing center for the mission, responsible for building the Cassini orbiter and for operating the spacecraft throughout its long journey and its years of exploration. The Jet Propulsion Laboratory, often called simply JPL, had a long history of managing deep space missions, from the Mariner spacecraft that explored the inner planets to the Voyager probes that had given humanity its first close-up views of the outer solar system, and the engineers and scientists that brought decades of accumulated wisdom to the Cassini project. The European Space Agency was responsible for the Huygens probe, which was designed and built by a consortium of European aerospace companies and research institutions, drawing upon expertise from across the continent. The Italian Space Agency made a particularly significant contribution by providing the high-gain antenna that would serve as Cassini's primary means of communicating with Earth, a vital piece of hardware that required extraordinary precision in its design and construction. For the antenna would need to transmit data across billions of kilometers of empty space with remarkable fidelity. ACI also contributed significant portions of the radar system that would eventually peer through Titan's opaque atmosphere to reveal the Moon's hidden surface. The total cost of the Cassini-Huygens mission, when all contributions from all partners were accounted for, came to approximately $3.26 billion, a figure that reflected the enormous complexity of the undertaking and the many years of work that would be required to bring it to fruition. This cost was spread across the partner agencies and across the nearly 2 decades that separated the mission's conception from its arrival at Saturn, and when calculated in terms of the scientific return that the mission would eventually provide, it represented a remarkable investment in human knowledge. More than 5,000 people across those 17 countries contributed to the mission in one way or another, from the scientists who defined the questions that Cassini would seek to answer, to the engineers who designed and built the spacecraft and its instruments, to the technicians who assembled the components with painstaking care, to the administrators who navigated the political and budgetary challenges that arose along the way. Each of these individuals added their own small contribution to the whole, and the spacecraft that eventually emerged was the product of their collective effort, a testament to what can be accomplished when nations choose to work together in the pursuit of understanding. The physical assembly of the Cassini spacecraft took place at the Jet Propulsion Laboratory's Spacecraft Assembly Facility, a specialized building where the cleanest possible conditions are maintained to protect sensitive equipment from contamination. Between 1995 and 1997, technicians in specialized garments worked methodically to bring together the many components that would make up the finished spacecraft, connecting cables, mounting instruments, and testing systems with the careful attention to detail that deep space missions demand. The assembly process was itself a kind of choreography, with each step following logically from the last according to plans that had been refined over many iterations, and the workers moved through the facility with the unhurried precision of people who understood that a single mistake could compromise a mission that had consumed years of effort and billions of dollars. The Huygens probe arrived from Europe and was mated to the Cassini orbiter. The two spacecraft joined together for a journey that would take them across the solar system before they finally parted ways in the skies above Titan. The Cassini orbiter carried 12 scientific instruments, each designed to study a different aspect of the Saturnian system. These instruments included cameras that could capture images in visible light and in other portions of the electromagnetic spectrum, spectrometers that could analyze the composition of atmospheres and surfaces by examining the light they emitted or reflected, magnetometers that could map the magnetic fields surrounding Saturn and its moons, and instruments designed to study the particles and plasma that filled the space around the planet. There was a radar system capable of penetrating the thick clouds of Titan to reveal the surface below, and there were instruments designed to study the structure of Saturn's rings in unprecedented detail, measuring the sizes and compositions of the countless particles that made up those iconic features. Each instrument represented years of development by teams of scientists and engineers, and each was designed to answer specific questions while also remaining flexible enough to respond to unexpected discoveries. The Huygens probe, smaller than its partner but no less sophisticated in its way, carried 6 instruments of its own, chosen specifically for the task of studying Titan's atmosphere and surface during the brief hours of its descent. These instruments would measure the temperature, pressure, and composition of the atmosphere at different altitudes, analyze the aerosols and clouds that gave Titan its distinctive orange color, listen for sounds that might reveal information about the environment, and capture images of the surface as it rushed up to meet the descending probe. The designers of Huygens had to account for the possibility that the probe might land on a solid surface or splash down into a liquid sea, for at the time of the mission's design, no one knew for certain what conditions awaited on Titan's hidden surface. This uncertainty required a kind of engineering flexibility, a willingness to prepare for multiple outcomes while hoping that the probe would survive long enough to return at least some data to the orbiter passing overhead. As the assembly work progressed through those years in the mid-1990s, the spacecraft gradually took shape, transforming from components and plans into a tangible object that would soon carry human curiosity to the outer reaches of the solar system. The dream that had begun as proposals exchanged between scientific institutions in 1982 was becoming real, assuming physical form in a clean room in Pasadena where technicians worked with quiet concentration. All the political battles, all the budget negotiations, all the international agreements and technical compromises had led to this: a spacecraft being readied for a journey that would take 7 years simply to reach its destination, and then more than a decade to complete its work. The people who had shepherded the mission through its many challenges could look upon the spacecraft and see their efforts made manifest, knowing that soon it would leave the Earth behind and begin its long, slow voyage toward Saturn, carrying with it the instruments that would finally answer questions that had been asked for centuries, ever since Huygens first spotted Titan and Cassini first glimpsed the gap in Saturn's rings. On the morning of October 15th, 1997, the sky above Cape Canaveral was clear and still, the kind of morning that seems almost ordinary until you remember what is about to happen. And even then, the ordinariness persists in a way that is rather comforting if you think about it, because the most extraordinary human endeavors so often begin in just this sort of quiet, unremarkable weather. At Launch Complex 40, a Titan IVB rocket stood waiting on its pad, a vehicle that measured approximately 56 meters in height and weight. When fully loaded with its fuel and its precious cargo, somewhere in the region of 1 million kilograms, though of course the exact figures varied depending on the specific configuration and the moisture content of the air and all those small variables that engineers must account for in their careful, patient calculations. The Centaur upper stage sat atop the Titan, and atop that, enclosed within its protective fairing, was the Cassini spacecraft, joined to its companion, the Huygens probe, which had been built by the European Space Agency and which would one day descend through the thick orange atmosphere of Saturn's moon Titan, though that day was still nearly 8 years in the future, a span of time that seems quite long when you are waiting for something and quite short when you look back upon it. The launch window opened at 4:55 in the morning, Eastern Daylight Time, and the controllers at Kennedy Space Center proceeded through their checklists with the measured calm that characterizes such operations, each step verified and confirmed in quiet voices that carried across the communication loops, voices that had rehearsed these procedures many times before and would do so again in the years to come. The Titan IVB was, at that time, the most powerful unmanned rocket in the American fleet, capable of lifting heavy payloads into trajectories that would carry them beyond Earth's gravitational influence and out into the solar system, where distances are measured not in kilometers or miles but in the time it takes for light itself to traverse them. At 4:43 in the morning, some 12 minutes before the scheduled liftoff, the launch team confirmed that all systems were nominal, a word that in aerospace parlance simply means that everything is behaving as expected, which is to say, behaving well. The rocket lifted off the pad at 4:43 a.m., rising on a column of flame that illuminated the Florida coastline in shades of orange and white, and as it climbed through the atmosphere, it followed a trajectory that had been calculated with extraordinary precision, accounting for the rotation of the Earth and the positions of the planets and the gravitational influences that would shape the spacecraft's path over the coming years. The Titan's solid rocket boosters burned for approximately 2 minutes before separating and falling away into the Atlantic Ocean, and the core stage continued to push the vehicle higher, until it too exhausted its fuel and separated, leaving the Centaur upper stage to complete the work of placing Cassini on its interplanetary trajectory. The Centaur fired twice, first to achieve a parking orbit around the Earth and then, approximately 22 minutes after launch, to accelerate the spacecraft to the velocity required to escape Earth's gravity and begin its long journey outward. But the launch of Cassini had not proceeded without controversy, and indeed, in the weeks and months leading up to that October morning, there had been considerable public debate about the wisdom of sending this particular spacecraft into space at all, a debate that centered not on the scientific value of the mission, which was widely acknowledged, but on the nature of its power source. The Cassini spacecraft carried 3 radioisotope thermoelectric generators, devices that convert the heat produced by the natural decay of radioactive material into electrical power, and these generators contained a total of approximately 72 pounds of plutonium-238, which is to say about 32.8 kilograms, an amount that represented the largest quantity of this particular isotope ever launched into space by the United States. Plutonium-238 is not the same as plutonium-239, which is the isotope used in nuclear weapons, and it cannot be used to create a nuclear explosion, but it is nonetheless a radioactive material, and its presence on board the spacecraft raised concerns among certain members of the public who worried about what might happen if the launch failed and the plutonium were released into the environment. The Florida Coalition for Peace and Justice was among the most vocal of the groups that organized protests against the Cassini launch, and in the days and weeks before October 15th, demonstrators gathered near the Kennedy Space Center to express their opposition to what they described as an unacceptable risk to public health and safety. The coalition, which had been founded some years earlier to address issues related to nuclear weapons and nuclear power, argued that the potential consequences of an accident were too severe to justify the mission, regardless of its scientific merits, and they called upon NASA to cancel the launch or to find an alternative power source that did not involve radioactive materials. Other individuals and organizations joined in these protests, including some scientists who questioned the safety analyses that NASA had conducted, and for a time, the debate over Cassini received considerable attention in the news media, with stories appearing in newspapers and on television programs that reached audiences far beyond the usual community of space enthusiasts. NASA, for its part, had anticipated these concerns and had conducted extensive safety analyses long before the launch date arrived. The agency's risk assessment concluded that there was approximately a 1 in 1,500 chance that an accident during launch could result in the release of some portion of the plutonium into the environment, a probability that the agency considered acceptably low given the importance of the mission and the safeguards that had been incorporated into the design of the radioisotope thermoelectric generators. These generators were encased in multiple layers of protective material, including iridium metal and graphite, designed to contain the plutonium even in the event of a catastrophic failure of the launch vehicle, and tests had shown that the casings could withstand impacts and explosions and fires of considerable intensity without releasing their contents. The plutonium itself was in the form of ceramic pellets, a form chosen specifically because it would not vaporize or disperse easily if the containment were breached, and the pellets were small enough that even if some were released, they would not travel far from the accident site. NASA acknowledged that no human endeavor is entirely without risk, but the agency maintained that the benefits of the Cassini mission, In terms of the scientific knowledge it would provide about Saturn and its moons, justified the very small probability of harm. The launch proceeded without incident, and the protesters who had gathered outside the Kennedy Space Center watched as the Titan IVB rose into the pre-dawn sky and disappeared into the darkness above, carrying its cargo of scientific instruments and plutonium alike on the first leg of a journey that would eventually span more than 2.2 billion miles. But the controversy over Cassini's radioisotope thermoelectric generators did not end with the successful launch, for there remained one more event that would bring the issue back into public attention, an event that would occur nearly 2 years later, when the spacecraft returned to the vicinity of Earth for a gravity assist maneuver. In the intervening months, Cassini traveled first toward the inner solar system, passing by Venus twice to gain the gravitational boost it needed to reach Saturn. The first Venus flyby occurred in April of 1998, when the spacecraft passed within approximately 284 kilometers of the planet's cloud tops, and the second occurred in June of 1999, when it approached to within about 600 kilometers. These flybys were not scientific observations in the usual sense, though the spacecraft's instruments did collect some data about Venus as it passed, but rather navigational maneuvers, using the gravity of Venus to bend the spacecraft's trajectory and increase its velocity, much as a ball thrown against a moving train will bounce back with greater speed than it had when it was thrown. The physics of gravity assists had been well understood since the 1960s, when mission planners first recognized that spacecraft could use the gravitational fields of planets to change their orbits without expending any fuel, and by 1997, such maneuvers had become a routine part of interplanetary mission design, employed by numerous spacecraft to reach destinations that would otherwise have required impractically large rockets to achieve directly. The Earth flyby was scheduled for August 18, 1999, and as that date approached, the concerns that had been raised before the launch resurfaced in the public discourse, though with somewhat different emphasis. The spacecraft would pass within approximately 727 miles of the Earth's surface, which is to say about 1,171 kilometers, a distance that may sound quite large when compared to the distances we travel in our daily lives, but that is actually quite close when one considers the vastness of space and the difficulty of predicting with perfect accuracy the trajectory of an object traveling at thousands of miles per hour. Some critics argued that if anything went wrong, if the spacecraft's trajectory were even slightly different from what had been calculated, or if it encountered an unexpected obstacle, it might enter the Earth's atmosphere and burn up, releasing its plutonium into the air where it could be dispersed by winds and inhaled by people on the ground. The probability of such an event was extremely small, far smaller even than the probability of an accident during launch, but it was not zero, and for some, any probability of catastrophic harm was too great to accept. NASA responded to these concerns with a renewed effort at public communication, explaining once again the safety measures that had been incorporated into the spacecraft's design and the extensive calculations that had been performed to ensure that the flyby would proceed safely. The agency noted that the spacecraft's trajectory had been planned with extreme care, and that even if the navigation were less accurate than expected, the probability of the spacecraft entering the Earth's atmosphere was vanishingly small, on the order of 1 in 1 million or less. Moreover, even in the extraordinarily unlikely event that the spacecraft did enter the atmosphere, the radioisotope thermoelectric generators were designed to survive re-entry intact, containing their plutonium rather than releasing it, and tests had demonstrated that the protective casings could withstand the heat and stress of atmospheric entry at speeds far greater than Cassini would be traveling. The flyby occurred as planned on August 18, 1999, and the spacecraft passed over the Earth without incident, its instruments briefly observing the planet that had sent it forth and then turning once again toward the outer solar system, where its true destination awaited. The journey continued through the darkness of interplanetary space, the spacecraft traveling at speeds that varied depending on its position relative to the Sun and the planets, sometimes moving faster and sometimes slower as the gravitational influences of the solar system acted upon it. In December of 2000, Cassini passed by Jupiter, the largest planet in our solar system, a world of swirling clouds and intense radiation and a retinue of moons that numbers well into the dozens. The Jupiter flyby provided another gravity assist, bending the spacecraft's trajectory and increasing its speed for the final leg of the journey to Saturn. But it also provided an opportunity for scientific observation, and Cassini's instruments collected data and images of Jupiter that complemented the observations being made at the same time by another spacecraft, the Galileo probe, which had been orbiting Jupiter since December of 1995. The two spacecraft, Cassini and Galileo, observed Jupiter from different vantage points, providing scientists with a stereoscopic view of the planet and its moons that would not have been possible with a single observer. Cassini photographed the Great Red Spot, that enormous storm that has been swirling in Jupiter's atmosphere for centuries, and it observed the thin rings that encircle the planet, rings that are far less prominent than Saturn's but that are nonetheless present and interesting in their own right. It captured images of the Galilean moons, those four large satellites that Galileo Galilei had first observed in 1610, and it measured the magnetic field and the charged particles that fill the space around Jupiter, data that would help scientists understand the complex interactions between the planet and its environment. And then, its observations complete, Cassini continued on its way, leaving Jupiter behind and heading out toward the cold, distant region of the solar system where Saturn orbits the Sun. The total distance traveled by Cassini from its launch in October of 1997 to its arrival at Saturn in July of 2004 was approximately 2.2 billion miles, a number that is difficult to comprehend in any intuitive sense, for it is so far beyond the scale of human experience that it becomes almost abstract, a figure to be written down and acknowledged rather than truly understood. If you were to drive a car at highway speeds, never stopping for fuel or rest, it would take you more than 4,000 years to cover that distance, and even light, the fastest thing in the universe, requires hours to traverse the vast expanses between the planets. But Cassini was patient, as spacecraft must be, and it traveled those 2.2 billion miles one moment at a time, its instruments dormant or active as the mission plan required, its radioisotope thermoelectric generators steadily converting the heat of decaying plutonium into the electrical power that kept its systems alive, until at last, after 7 years of travel, it arrived at the ringed planet and prepared to begin the work for which it had been built. On the 1st of July, in the year 2004, a spacecraft that had been traveling for nearly 7 years across the vast and quiet distances of the outer solar system arrived at last at its destination. And what happened over the course of that single night, measured in the hours and minutes of clocks on Earth, represented one of the most delicate and consequential maneuvers ever attempted in the history of planetary exploration. The Cassini spacecraft, carrying with it the European-built Huygens probe, had crossed some 2 billion miles since its departure from Cape Canaveral in October of 1997, and now, as it approached the ring giant that had been its target all along, it needed to slow itself down just enough to be captured by Saturn's gravity, to transform itself from a passing visitor into a permanent resident of that distant system, orbiting among the moons and rings for what mission planners hoped would be many years of scientific observation. This process of slowing down and entering orbit is known as Saturn orbit insertion, abbreviated in the way of space missions to the simple letters SOI, and it required the spacecraft to fire its main engine for 96 minutes, a duration that may not sound particularly remarkable when spoken aloud, but which represents an extraordinarily long burn by the standards of deep space navigation. During those 96 minutes, the engine would need to function without falter, reducing the spacecraft's velocity by approximately 626 meters per second, and there was no possibility of a second attempt, no backup plan that could rescue the mission if something went wrong, because the geometry of the encounter and the fuel remaining aboard the spacecraft allowed for only this single, carefully calculated opportunity to enter orbit around Saturn. In the weeks before this critical night, Cassini had already begun its scientific work, taking advantage of the long approach to observe objects that would become more difficult to study once the spacecraft settled into orbit. On the 11th of June, 3 weeks before Saturn orbit insertion, the spacecraft made a close flyby of a small, distant moon called Phoebe, passing within approximately 2,000 kilometers of its irregular, crater-pocked surface. This was the first close examination of Phoebe ever conducted, and the images and data returned revealed a world quite different from the other moons of Saturn, a dark and ancient body whose composition and orbit suggested that it had not formed alongside Saturn at all, but had instead wandered in from the outer reaches of the solar system, from that distant reservoir of icy objects known as the Kuiper Belt, and had been captured by Saturn's gravity at some point in the remote past. Phoebe's surface, as revealed in those June images, was heavily cratered and marked with what appeared to be layers of ice and darker organic material, and its density and composition pointed to origins far beyond the orbit of Neptune, among the frozen remnants of the solar system's formation. The discovery confirmed what some scientists had suspected for years, that Saturn's outermost satellites might include objects that had spent billions of years in the cold darkness of the outer solar system before drifting inward and finding themselves trapped in orbit around the ring planet. It was a gentle preview of the scientific riches that awaited, a small taste of what Cassini would reveal once it began its proper tour of the Saturnian system. But before that tour could begin, the spacecraft had to survive the night of July 1st, and the maneuvers required for Saturn orbit insertion were among the most perilous ever designed for a robotic explorer. The trajectory called for Cassini to pass through a gap in Saturn's ring system, threading its way between two of the fainter outer rings known as the F ring and the G ring, a passage that no spacecraft had ever attempted before. The rings of Saturn, though they appear as solid structures in photographs, are composed of countless individual particles of ice and rock, ranging in size from tiny grains no larger than sand to chunks as big as houses, and even in the relatively sparse regions between the main rings, there existed the possibility of collision with debris that could damage or destroy the spacecraft. To protect itself during this crossing, Cassini was oriented so that its large high-gain antenna faced forward, serving as a shield against any small particles that might be encountered during the passage through the ring plane. This configuration meant that the antenna could not be pointed toward Earth, and so, for a period of approximately 84 minutes, the spacecraft would be out of contact with mission controllers, unable to send telemetry or receive commands, alone in the most literal sense as it performed the most critical operations of its 7-year journey. On Earth, in the mission control room at the Jet Propulsion Laboratory in Pasadena, California, the team that had built and guided Cassini through the long years of cruise waited through those minutes of silence with a particular kind of patience that comes only from experience with the timescales of deep space exploration. Robert Mitchell, who served as the project manager, monitored the consoles and displays that would eventually show whether the spacecraft had survived its passage and successfully completed the orbit insertion burn. though there was nothing he or anyone else could do during the blackout except wait and trust in the engineering that had brought them this far. The communications blackout was not an unexpected consequence of some emergency or malfunction, but rather a planned and accepted part of the mission design. A recognition that the geometry of the orbit insertion required the spacecraft to prioritize its own protection over its ability to report home. During those 84 minutes, Cassini crossed through the ring plane twice, once on the way in towards Saturn and once on the way out, and at its closest approach, the spacecraft passed within approximately 20,000 kilometers of Saturn's cloud tops, a distance of roughly 12,400 miles, closer to the planet than any spacecraft had ever ventured before. At that proximity, Saturn would have filled the sky, its banded atmosphere of hydrogen and helium swirling in storms and jet streams that have persisted for centuries. Though of course there was no human eye aboard to witness the view, only instruments and cameras that would record what they could while the spacecraft attended to the urgent business of firing its engine and adjusting its trajectory. The main engine burn began as planned, and over the course of an hour and 36 minutes, it changed the velocity of the spacecraft by just enough to transform its path from a hyperbolic trajectory that would have carried it past Saturn and back out into interplanetary space, into an elliptical orbit that would keep it bound to the planet for years to come. When the blackout ended and telemetry began flowing once more from Cassini to the receiving stations of the Deep Space Network, the data confirmed what the mission team had hoped but could not know for certain until that moment: that the engine burn had completed successfully, that the spacecraft had survived its passage through the ring plane without significant damage, and that Cassini was now in orbit around Saturn, the first spacecraft ever to take up residence in that distant system. In the control room at JPL, the confirmation was met with applause and embraces, with the particular kind of celebration that follows years of effort and weeks of mounting tension. Though in the manner of these things, the celebration was also tempered by the awareness that the mission was only beginning, that the orbit insertion was merely the necessary first step in a scientific program that would extend for years into the future. Similar scenes unfolded at the European Space Agency's Operations Center in Darmstadt, Germany, where engineers and scientists who had worked on the Huygens probe and various instruments aboard Cassini gathered to watch the progress of the orbit insertion. The mission was an international collaboration of unusual scope, involving NASA, the European Space Agency, and the Italian Space Agency, along with scientific teams from more than a dozen countries, and the successful arrival at Saturn represented a triumph shared across continents and time zones, a moment of collective achievement in the long human project of exploring the solar system. In the hours and days following the orbit insertion, as the mission team analyzed the data returned during the close approach, they discovered something unexpected in the images captured by Cassini's cameras: evidence of two small moons that had not been seen before, faint points of light moving against the background of stars in a manner that indicated they were orbiting Saturn rather than passing through the frame by coincidence. These objects were eventually confirmed as new members of the Saturnian system and were given the names Methane and Pallene, adding to the ever-growing census of moons that circle the ringed planet, which would continue to expand throughout Cassini's years of operation. The discovery of new moons during such a critical phase of the mission was a reminder that even at moments of maximum operational intensity, the scientific work of exploration continues, that the instruments aboard a spacecraft do not distinguish between routine observations and historic maneuvers, recording whatever falls within their view with the same patient fidelity regardless of what the humans back on Earth might be feeling at any given moment. Methane and Pallene proved to be small, icy bodies, each only a few kilometers across, occupying orbits between the larger moons Mimas and Enceladus, and their discovery was among the first of many surprises that Cassini would deliver over its long mission. The orbital path established by the July 1st insertion burn was not the final orbit that Cassini would occupy, but rather the first of many, a highly elliptical loop that took the spacecraft far from Saturn before bringing it back for subsequent close approaches. Over the years that followed, a series of carefully planned maneuvers and gravity assists from Saturn's moons would reshape this orbit again and again, allowing Cassini to explore different regions of the system, to pass close by moons that would never be visited otherwise, and to observe the rings and atmosphere from angles and distances that revealed new details invisible from any other vantage point. But all of that lay in the future, beyond the scope of this particular night, which was concerned only with the question of whether the spacecraft would survive long enough to begin its work. The answer, as confirmed by the telemetry flowing back through the Deep Space Network, was yes, and with that confirmation, the Cassini-Huygens mission entered a new phase. No longer a spacecraft in transit, but a permanent outpost of human curiosity in orbit around the second-largest planet in the solar system. The ring crossing itself, that passage through the gap between the F and G rings that had caused such concern during the planning stages, proved in the end to be uneventful. The particles in that region sparse enough that the spacecraft passed through without detectable impact. The forward-facing antenna served its purpose as a shield, and the delicate instruments and solar panels emerged undamaged, ready to begin the observations that would occupy them for years to come. It was, in the end, an anticlimax of the most welcome sort, the kind of non-event that allows a mission to proceed according to plan. Though those who had worked through the long hours of the blackout would remember the weight of uncertainty that had filled those minutes when no one on Earth could know whether their spacecraft was intact or had been silently destroyed by a fragment of ice no larger than a pebble. And so, with the engine burn completed and the orbit confirmed, with 2 new moons already discovered and the promise of countless more revelations ahead, the Cassini spacecraft settled into its new home among the rings and moons of Saturn, and the long work of exploration began in earnest, patient and methodical, one orbit at a time, one observation after another, building slowly toward a portrait of a world that humans had wondered about for as long as they had looked up at the wandering lights in the night sky. And so we come now to the Huygens probe, that small and patient traveler which had journeyed for 7 years while attached to the side of Cassini, waiting quietly for the moment when it would separate and begin its own brief but remarkable mission, a descent through the thick orange atmosphere of Titan and, if all went well, a landing upon the surface of a world that no human-made object had ever touched before, this being a moon of Saturn located so very far from the warmth of the sun that liquid methane falls as rain there and pools into lakes and carves channels through terrain made not of rock but of water ice as hard as stone in that profound and distant cold. The separation occurred on the 25th of December in the year 2004, which is to say Christmas Day for much of the world, though the engineers and scientists at the European Space Agency were thinking less of holiday festivities and more of the careful sequence of events that would send Huygens on its way. The pyrotechnic devices firing as planned, the gentle springs pushing the probe away from Cassini at a speed of roughly 30 centimeters per second, which is about the pace of a very slow walk, and then the 2 spacecraft drifting apart in the darkness of space, Cassini turning to watch its companion recede, taking photographs to confirm that the separation had occurred correctly, that Huygens was rotating as expected to maintain its stability, and that the coast phase had begun. For the next 20 days, Huygens traveled alone through space, spinning slowly, carrying no propulsion of its own, following a trajectory that had been calculated years in advance and refined through careful observations during the long journey from Earth, The probe equipped with 2 redundant timers that would wake it from its dormant state at the appropriate moment. Though, of course, the engineers could not speak to it during this time, nor could they adjust its course in any way. The probe committed now to its path like a stone thrown across a pond, subject only to the laws of gravity and motion that Isaac Newton described so long ago, and that continue to govern the movements of objects both great and small throughout our solar system. During this coast huygens Cassini performed a deflection maneuver, adjusting its own trajectory so that it would be in the correct position to receive the transmissions from Huygens as the probe descended through Titan's atmosphere. This being necessary because Huygens could not communicate directly with Earth, the distances being too great and the probe too small to carry an antenna powerful enough for such a task. And so all of the data that Huygens would collect, all of the measurements and images and sounds, would need to be relayed through Cassini back to the listening dishes on Earth, a chain of communication stretching across more than 1 billion kilometers of space, each link of which needed to function properly if the mission was to succeed. The morning of the 14th of January, 2005, arrived at the European Space Operations Center in Darmstadt, Germany, where the mission controllers had gathered to monitor the descent. Though there was little they could do at this point but wait and hope, the signals from Titan taking over an hour to reach Earth, which meant that by the time they received word that Huygens had begun its entry into the atmosphere, the probe would already have been descending for more than 60 minutes, the outcome already determined, the landing already accomplished or failed, the data either collected or lost, and yet still they waited. Because this is what one does when 7 years of work and hope are culminating in a single morning on a distant world. Jean-Pierre Le Breton, who served as the Huygens project scientist for the European Space Agency, found himself experiencing the particular mixture of anticipation and helplessness that comes with interplanetary exploration, the knowledge that everything was happening so very far away, that the probe was either functioning or it was not, that the parachutes were either deploying or they were not, and that nothing he or anyone else could do would change what was occurring at that moment in the thick nitrogen atmosphere of Titan, where Huygens was beginning its descent at a velocity of approximately 6 kilometers per second, the heat shield glowing with the friction of atmospheric entry, the temperature climbing to more than 1,000 degrees Celsius on the outer surface, while the instruments inside remained protected and cold, waiting for the moment when they would begin their work. The descent lasted 2 hours and 27 minutes in total, a duration that might seem brief after 7 years of travel, but which represented an extraordinary amount of time for a probe entering an atmosphere. This lengthy descent being possible because of Titan's thick atmosphere and low gravity, the combination allowing Huygens to drift slowly downward beneath its parachutes, gathering data all the while. And the probe carried 6 scientific instruments, each designed to study a different aspect of this mysterious moon, each with its own particular contribution to make to our understanding of this world where the chemistry of life might be unfolding in ways we do not yet comprehend. The first of these instruments was called HAZY, which stands for Huygens Atmospheric Structure Instrument, and its purpose was to measure the physical properties of Titan's atmosphere during the descent, recording the temperature and pressure and density at different altitudes, building up a profile of the atmosphere from the outer reaches down to the surface, this being fundamental information that scientists needed in order to understand how Titan's atmosphere behaves, how it circulates, how it changes with altitude, and how it compares to the atmospheres of other worlds including our own Earth, which has a nitrogen-rich atmosphere as well, though Earth's atmosphere is much thinner and contains oxygen as a significant component, which Titan's atmosphere does not. The second instrument was the gas chromatograph mass spectrometer, known as GCMS, and this device was designed to analyze the chemical composition of the atmosphere, separating the various gases and identifying them with great precision, determining not only what molecules were present but how much of each one there was. This being important work because Titan's atmosphere contains a complex mixture of organic compounds, hydrocarbons and nitriles and other molecules that form when ultraviolet light from the sun interacts with the methane and nitrogen in the upper atmosphere, creating a kind of photochemical smog that drifts slowly downward and eventually settles on the surface below. The third instrument bore the name Aerosol Collector and Pyrolyzer, or ACP, and its function was to capture samples of the small particles suspended in Titan's atmosphere, the tiny droplets and solid particles that give the atmosphere its orange color and make the surface so difficult to see from space. And once these particles were captured, the instrument would heat them and analyze the gases that were released, providing information about what these aerosols were made of and how they might have formed in the upper atmosphere before beginning their long, slow fall toward the surface. The fourth instrument was the Descent Imager and Spectral Radiometer, known as GSR, and this was perhaps the most anticipated of all the instruments because it included cameras that would take pictures during the descent, revealing for the first time what Titan's surface actually looked like beneath that impenetrable orange haze. And in addition to the cameras, DASR included spectrometers that would measure the light at different wavelengths, helping scientists understand what materials were present on the surface, and a lamp that would illuminate the ground during the final moments before landing, allowing images to be taken even in the dim light that reaches Titan's surface, where the sun appears as merely a bright spot in a dark orange sky. The fifth instrument was the Doppler Wind Experiment, abbreviated as DWE, and this instrument measured the winds that pushed Huygens from side to side during its descent, using precise measurements of the radio signal sent from the probe to Cassini to determine how fast Huygens was being blown by the winds and in which direction. This information helping scientists understand the atmospheric circulation patterns on Titan, the way the air moves from one region to another, the way weather systems might develop and dissipate on this cold and distant world. The sixth and final instrument was the Surface Science Package, or SSP, which was designed to study whatever Huygens landed upon, whether solid ground or liquid ocean, the scientists not knowing in advance which it would be. And so the instrument included sensors that could measure the properties of a liquid if Huygens splashed down into a methane lake, as well as sensors that could measure the properties of a solid surface if the probe landed on terrain. And, as it happened, Huygens landed on something that was neither entirely liquid nor entirely solid, but rather a surface that had the consistency of wet sand or perhaps packed snow, yielding slightly under the weight of the probe before providing a stable platform upon which Huygens could rest and continue its observations. Now it must be mentioned that the descent did not proceed entirely as planned, for there was a difficulty with the communications link between Huygens and Cassini, a problem that had been discovered some years earlier by careful observers including amateur radio operators who had been tracking the spacecraft's signals from Earth. Among them a German amateur named Erich Leitgeb who noticed certain irregularities in the way the signal was being handled. And upon investigation, it was found that there was a software error that would prevent one of the two redundant communication channels from functioning properly, the command to turn on the receiver on Cassini never having been included in the sequence of operations, a small but significant oversight that meant half of the data collected by Huygens would be lost. The European Space Agency worked to mitigate this problem as much as possible, and the mission proceeded with the knowledge that only one channel would be operating, which meant that some of the data would indeed be lost. And yet the mission was still able to achieve its primary objectives, still able to return images and measurements that revolutionized our understanding of Titan. And perhaps there is a lesson here about the importance of careful review and the value of independent observers who check and double-check the work. Even observers who are not professionals but simply enthusiasts with radio equipment and a passion for space exploration, their contributions proving essential to the success of this mission. The images that came back from Huygens revealed a world that was both alien and strangely familiar, the surface showing a terrain of orange and brown tones, with dark channels that appeared to have been carved by flowing liquid. These channels resembling the river valleys and drainage networks that one sees on Earth, though on Titan the liquid that carved them was not water but methane, which exists in liquid form at the extremely low temperatures found there, approximately 179 degrees Celsius below zero, a temperature at which water ice becomes as hard as granite, and methane behaves much as water does on our own world, evaporating into the atmosphere, forming clouds, falling as rain, and flowing across the surface to collect in lakes and seas. Near the landing site, the cameras revealed a surface strewn with rounded pebbles and cobbles, these being stones that had clearly been shaped by the action of flowing liquid, their edges worn smooth in the same way that river rocks are worn smooth on Earth, and the composition of these pebbles was determined to be water ice rather than silicate rock, for on Titan it is water ice that plays the role that rock plays on Earth, forming the solid foundation of the landscape, while methane and ethane play the role that water plays here, moving through a cycle of evaporation and precipitation that shapes the surface over vast spans of time. The Huygens probe continued to operate on the surface of Titan for 72 minutes, which far exceeded the planned minimum of 3 minutes, the engineers having designed the probe to survive landing and transmit for at least that brief period, but having hoped for more. And they received far more than they had dared to hope. More than an hour of data from the surface of a world that lies nearly 1.5 billion kilometers from Earth, the batteries slowly draining, the instruments continuing to function, the data continuing to flow back to Cassini overhead and then onward to the listening stations on Earth, until finally the signal faded and Huygens fell huygens, its mission complete, its work done, its contribution to human knowledge assured. Among the data returned by Huygens were recordings of sound, the microphone on the descent imager having captured the noise of the probe's descent through the atmosphere. And when these recordings were processed and made audible, listeners could hear the whisper of Titan's winds, a soft rushing sound that continued throughout the descent, the voice of an alien atmosphere speaking across the vast distance of space, reminding us that these distant worlds are real places with real weather and real landscapes, places where a microphone can record the sound of wind and transmit it back to human ears, places that are no longer merely points of light in the night sky but worlds that we have visited, however briefly, and begun to understand. And now we turn our attention to a world that revealed itself slowly, flyby by flyby, through the patient accumulation of data gathered over nearly 2 decades of careful observation. Titan, the largest of Saturn's moons, had long presented itself as little more than a featureless orange sphere to the telescopes of Earth, its surface hidden beneath a thick and hazy atmosphere that scattered visible light and kept its secrets well concealed. But Cassini carried instruments designed specifically to peer through that murky veil. And what those instruments revealed, over the course of 127 dedicated flybys, was nothing less than a complete and complex world, one with flowing rivers and standing lakes and weather systems that moved with the slow patience of an alien climate operating on timescales quite different from our own. The atmosphere of Titan is composed primarily of nitrogen, much like the atmosphere of Earth, though it is far colder and contains no free oxygen to speak of. What it does contain, in meaningful quantities, is methane, and it was this simple hydrocarbon molecule that would prove to be the key to understanding the remarkable processes unfolding on Titan's surface. At the temperatures found on this distant moon, hovering around -179 degrees Celsius. Methane behaves not as a gas but as a liquid and, under certain conditions, as a solid. This means that on Titan, methane can rain from the sky, can flow across the surface in rivers and streams, can collect in low-lying basins to form lakes and seas, and can evaporate back into the atmosphere to begin the cycle again. It is a hydrological cycle in every meaningful sense of the term, complete with precipitation and runoff and evaporation. Only the working fluid is not water but liquid hydrocarbons, and the whole system operates at temperatures that would freeze water as solid as granite. The first confirmed observation of a standing body of liquid on Titan's surface came in 2007, when Cassini's radar instrument detected a dark, smooth feature near the Moon's south pole that showed all the characteristics one would expect from a lake of liquid hydrocarbons. This feature was subsequently named Ontario-Lacus, after Lake Ontario on Earth, and it measured approximately 235 kilometers in its longest dimension, making it comparable in size to its terrestrial namesake. The radar signature was unmistakable, showing the kind of smooth, mirror-like return that indicates a flat liquid surface, and subsequent observations confirmed that the feature was indeed a lake, filled with a mixture of liquid methane and liquid ethane in proportions that would vary somewhat with the seasons. Ontario-Lacus became the first confirmed lake to be discovered on any world other than Earth, and its identification marked the beginning of a sustained campaign to map and understand the full extent of Titan's liquid features. As Cassini continued its methodical reconnaissance of Titan, executing flyby after flyby at varying altitudes and on varying trajectories, a remarkable picture began to emerge. The Moon's polar regions, it turned out, were home to an extensive network of lakes and seas, with the largest of these liquid bodies concentrated near the North Pole. The names assigned to these features were drawn from mythology and legend, as is the tradition for extraterrestrial geography, and they evoked a sense of ancient mystery that seemed fitting for such alien landscapes. Ligeia Mare, named for one of the sirens of Greek mythology, was found to be the second largest body of liquid on Titan, covering an area of approximately 126,000 square kilometers. Its shores were irregular and complex, carved by what appeared to be river channels that fed into the sea from the surrounding highlands, and its depth was eventually measured at over 170 meters in some locations. But even Ligeia Mare was dwarfed by the largest of Titan's seas, a vast body of liquid hydrocarbons known as Kraken Mare. Named for the legendary sea monster of Scandinavian folklore, Kraken Mare sprawled across the northern polar region like a dark and ancient ocean, its total surface area exceeding 400,000 square kilometers. To put this in terrestrial terms, Kraken Mare is larger than the Caspian Sea on Earth, which is itself the largest enclosed body of water on our own planet. The shape of Kraken Mare is highly irregular, with numerous bays and inlets and what appear to be islands scattered throughout its extent. Rivers flow into it from the surrounding terrain, and its composition, like that of the smaller lakes, consists primarily of liquid methane and liquid ethane, with traces of dissolved nitrogen and other hydrocarbons mixed in. The presence of such a vast reservoir of liquid on a world so distant from the Sun seemed almost improbable when first detected, and yet there it was, mapped in exquisite detail by Cassini's radar, a sea that could swallow the largest lakes of Earth and still have room to spare. A fourth significant body of liquid was identified near the North Pole and given the name Punga Mare, after a Maori deity associated with ugly creatures and the ocean. Though smaller than Ligeia Mare or Kraken Mare, Punga Mare nonetheless represented a substantial reservoir of hydrocarbons, and its presence confirmed that the northern polar region was home to a diverse collection of liquid features ranging from small ponds to vast seas. Together, these four named bodies, Ontario Lacus in the south and Ligeia Mare, Kraken Mare, and Punga Mare in the north, formed the centerpieces of Titan's extraordinary liquid landscape, though hundreds of smaller lakes were also catalogued over the course of the mission. In 2009, Cassini captured an image that would become one of the most significant of the entire mission, though its beauty lay more in what it represented than in any visual drama. The spacecraft's visual and infrared mapping spectrometer detected a bright glint of reflected sunlight emanating from a location in the northern polar region, and upon analysis, this glint was confirmed to be sunlight reflecting off the smooth surface of Kraken Mare. It was the first direct observation of sunlight glinting off a body of liquid on any world other than Earth, a moment of quiet but profound significance for planetary science. The observation was possible because the sun had risen high enough in Titan's northern sky, as the seasons slowly progressed, to illuminate the northern lakes at an angle that would reflect light back toward the spacecraft. The glint was specular in nature, meaning it came from a surface that was smooth and flat on the scale of the light's wavelength, just as sunlight glints off the calm surface of a lake on Earth when viewed from an aeroplane. This single observation confirmed in the most direct way possible what the radar mapping had already strongly suggested, that Titan possessed actual liquid on its surface, not merely damp patches or underground reservoirs, but standing bodies of liquid open to the alien sky. The composition of these lakes and seas was determined through a combination of spectroscopic analysis and theoretical modeling. The liquid is predominantly methane, with significant amounts of ethane mixed in, along with smaller quantities of propane, hydrogen cyanide, and other organic compounds. This composition makes Titan's lakes quite different from any body of liquid on Earth. Water, the universal solvent of terrestrial chemistry, is entirely absent from these hydrocarbon seas. Instead, the lakes of Titan are pools of cryogenic organic liquid, cold enough to liquefy gases that would be invisible vapors on Earth. The ethane in particular is interesting, as it is produced continuously in the upper atmosphere by the breakdown of methane under the influence of ultraviolet radiation from the sun. This photochemical process converts methane into ethane and other more complex hydrocarbons, which then rain down onto the surface and accumulate in the low-lying basins to form the lakes we observe today. The lakes are thus not static features but dynamic components of a planetary chemistry that is constantly cycling material between the surface and the atmosphere. Over the 13 years of Cassini's presence in the Saturn system, the mission witnessed seasonal changes on Titan that unfolded with a slow and stately grace. Saturn, and by extension its moons, takes approximately 29 Earth years to complete a single orbit around the Sun, which means that the seasons on Titan last for roughly 7 Earth years each. When Cassini arrived in 2004, the northern hemisphere of Titan was in the grip of winter, with the North Pole shrouded in darkness and the southern hemisphere bathed in relative warmth. Over the following years, as Saturn progressed along its orbit, the seasons shifted, and the northern hemisphere began to receive increasing amounts of sunlight, while the south moved toward its own long winter. Cassini watched this transition unfold, documenting the migration of cloud systems from the South Pole toward the north, the growth and shrinkage of individual lakes, and the formation of a vast polar vortex at the South Pole as that hemisphere cooled. The southern polar vortex became visible in 2012, forming as the southern autumn progressed and temperatures in that region began to drop. This vortex was a massive rotating storm system, analogous in some ways to the polar vortices observed on Earth, though operating under very different physical conditions. Its formation marked a clear transition in Titan's atmospheric circulation, as the global wind patterns adjusted to the changing distribution of solar heating. The clouds that had once clustered near the South Pole were seen to dissipate as the weather systems migrated northward, following the sun as it climbed higher in the northern sky. By the end of the mission, the North Polar region had become the site of most of the atmospheric activity, with clouds and storms appearing over the vast northern seas. This slow progression of seasons, observed over more than a decade of continuous monitoring, provided planetary scientists with an unprecedented view of how weather systems on a distant world respond to the changing angle of sunlight, and the data collected will inform models of Titan's climate for decades to come. Among the many curious features observed in Titan's seas, perhaps the most enigmatic were the so-called magic islands, transient bright features that appeared and disappeared in the radar images of Legeia Mare over a period of months and years. First noticed in 2013, these features seemed to come and go without explanation, sometimes visible in one radar pass and completely absent in the next. Their nature remained uncertain for some time, with various hypotheses proposed to explain their ephemeral presence. One possibility was that they represented floating or suspended solids, perhaps clumps of organic material or water ice that had somehow found their way into the liquid. Another suggestion was that they were waves or rough patches on the surface of the sea, created by winds that varied in intensity from one observation to the next. But the leading hypothesis, and the one that gathered the most support as the data accumulated, was that the magic islands were caused by bubbles of dissolved nitrogen fizzing out of the liquid as conditions changed. The idea is that nitrogen, which dissolves readily in the cold methane of Titan's seas, could come out of solution if the liquid were warmed slightly or if the pressure changed, much as carbon dioxide bubbles out of a carbonated drink when the cap is removed. These nitrogen bubbles, rising through the liquid or collecting near the surface, would create regions of varying density and reflectivity that could appear as bright transient features in the radar images. As the bubbles dissipated or the nitrogen redissolved, the features would fade away. This explanation fits well with what we know of the physics of Titan's lakes and provides a satisfying, if somewhat mundane, answer to the mystery of the magic islands. They are not islands at all, it seems, but rather patches of fizzing sea, bubbling gently in the cold alien night. In 2016, analysis of data from Cassini's mass spectrometer revealed the presence of vinyl cyanide molecules in Titan's upper atmosphere. Vinyl cyanide, also known as acrylonitrile, is a relatively simple organic molecule with the chemical formula CHCN, but it has attracted particular interest from astrobiologists because of its potential to form cell-like structures. On Earth, the membranes that enclose living cells are made of phospholipids, which are molecules that have a water-attracting head and a water-repelling tail. In the presence of water, these molecules spontaneously arrange themselves into spherical shells called vesicles, which provide the basic architecture for cellular life. But on Titan, where there is no liquid water, phospholipid membranes could not form. The discovery of vinyl cyanide raised the intriguing possibility that similar structures could form in the hydrocarbon seas of Titan, using this alternative molecule as the building block. Theoretical studies suggest that vinyl cyanide molecules could arrange themselves into small, flexible structures called azotosomes, which would be stable in liquid methane and could potentially serve as the membranes for hypothetical life forms adapted to Titan's extreme conditions. It must be emphasized that no evidence of life has been found on Titan, and the existence of azotosomes remains purely theoretical at this time. But the discovery of the necessary raw material in Titan's atmosphere was nonetheless a significant finding, one that expanded the range of possibilities for how life might arise and sustain itself on worlds very different from our own. Jonathan Leonine, a planetary scientist who has been deeply involved in the study of Titan throughout the Cassini mission, has drawn parallels between the prebiotic chemistry occurring on Titan today and the chemistry that may have occurred on Earth in the earliest stages of our planet's history, before life arose. The atmosphere of early Earth is thought to have contained significant amounts of methane and other hydrocarbons, and the chemical reactions occurring in that atmosphere may have produced many of the same organic molecules that Cassini detected on Titan. In this sense, Titan can be viewed as a kind of natural laboratory, a place where the chemistry of a primitive world is playing out in slow motion under conditions that allow us to observe and study it from afar. The 127 flybys of Titan that Cassini executed over the course of its mission provided a wealth of data that will keep scientists occupied for many years to come. Each flyby was carefully planned to maximize the scientific return, with the spacecraft executing precisely calculated maneuvers to bring its instruments to bear on specific targets of interest. Some flybys were designed to map previously unseen regions of the surface, while others focused on atmospheric measurements or gravity field determinations. The cumulative effect of all these observations was the construction of a remarkably detailed portrait of a world that had been almost completely unknown before Cassini's arrival. We now know that Titan has lakes and seas of liquid hydrocarbons, fed by rivers that flow down from highlands of water ice. We know that it has weather systems that change with the seasons, with clouds that form and dissipate and migrate across the globe in response to the shifting angle of sunlight. We know that its atmosphere is rich in organic molecules, some of which may be relevant to the chemistry of life. And we know that it remains, even after all this study, a world of deep mystery and quiet wonder, waiting patiently for the return of spacecraft that might one day explore its shores in person. Among the many moons of Saturn, there is one small world that would come to occupy an extraordinary place in our understanding of where life might exist beyond Earth. And this is the story of how a frozen moon no larger than the state of Arizona revealed itself to be one of the most remarkable places in the entire solar system. The moon is called Enceladus, named after a giant from Greek mythology, and when Cassini arrived at Saturn in 2004, this little world was considered interesting but not particularly exceptional among the many icy satellites orbiting the ringed planet. It measures only 313 miles across, making it small enough that you could drive its entire circumference in a single day on an earthly highway, and its surface reflects nearly all the sunlight that falls upon it, making it one of the brightest objects in the solar system. Scientists expected to find a frozen, geologically quiet world, a relic from the early solar system preserved in the deep cold of the outer planets, and what they found instead would transform our thinking about where life might take hold in the universe. The first hint that Enceladus might be more than a simple ball of ice came during a flyby in February of 2005, when Cassini's magnetometer detected something unexpected as the spacecraft passed near the moon. The instrument registered a subtle but unmistakable deflection in Saturn's magnetic field, a perturbation that suggested the presence of an atmosphere around this tiny world. This was puzzling because Enceladus is far too small to hold onto an atmosphere through gravity alone, the way Earth or even Titan can, and any gases surrounding such a small body would drift away into space relatively quickly. The presence of an atmosphere therefore implied that something must be actively replenishing it, that there must be some ongoing process releasing material into the space around Enceladus, And this simple observation set in motion a cascade of discoveries that no one had anticipated. The team adjusted the spacecraft's trajectory to take a closer look, and during a flyby in July of 2005, Cassini's cameras captured images that would become some of the most significant photographs in the history of planetary exploration. There, rising from the south polar region of Enceladus, were enormous plumes of material spraying outward into space, fountains of fine particles backlit by the distant sun and extending far above the moon's icy surface. The plumes originated from a series of 4 roughly parallel fractures in the ice, features that scientists came to call tiger stripes because of their appearance in thermal images, where they showed up as warmer than the surrounding terrain. These 4 fractures were given names drawn from cities along ancient trade routes, places where knowledge and goods had flowed between civilizations, and they were called Alexandria, Cairo, Baghdad, and Damascus. The name seemed fitting for features that would become conduits for knowledge flowing outward from a hidden interior world. The tiger stripes stretch across the south polar region of Enceladus, each one roughly 80 miles long and spaced about 25 miles apart from its neighbors, and thermal measurements revealed that they are significantly warmer than the rest of the moon's surface. While most of Enceladus exists at temperatures around -300 degrees Fahrenheit, the tiger stripes register temperatures that are warmer by more than 100 degrees, still bitterly cold by earthly standards but warm enough to indicate that heat is flowing up from below. The plumes themselves erupt along the length of these fractures, not as single continuous jets but as dozens of individual sources, and the material rises to remarkable heights before either escaping into space or falling back as fresh snow onto the moon's surface. This process of snowy fallback helps explain why Enceladus is so extraordinarily reflective, why it shines so brightly in the darkness of the outer solar system, and it suggests that the surface is being continuously renewed by material from below. As remarkable as the initial discovery was, the Cassini team recognized that to truly understand what was happening on Enceladus, the spacecraft would need to fly much closer, even through the plumes themselves. This was a prospect that required careful consideration, as flying through jets of material at high speed carries inherent risks to a spacecraft, and the engineers had to balance the scientific potential against the possibility of damage to sensitive instruments. In October of 2008, Cassini performed one of its most daring maneuvers, diving through the plumes at an altitude of just 15 miles above the surface of Enceladus. At this distance, the spacecraft passed through the densest part of the spray, its instruments sampling the material directly and analyzing its composition in ways that remote observation could never achieve. The spacecraft survived the passage without incident, and the data it collected would prove to be extraordinarily valuable. What Cassini found in the plumes was primarily water vapor and tiny particles of water ice, confirming that the eruptions were fundamentally aqueous in nature. But mixed in with the water were other compounds that told a more complex story about conditions beneath the icy surface. The spacecraft detected carbon dioxide and carbon monoxide, simple organic compounds like methane and propane, and more complex organic molecules that hinted at interesting chemistry occurring somewhere within Enceladus. There was also ammonia, which can act as an antifreeze in water, potentially keeping liquid water stable at much lower temperatures than would otherwise be possible. Each compound added another piece to the puzzle of what might be happening inside this small and seemingly unremarkable moon. In 2009, analysis of data from Cassini's cosmic dust analyzer revealed something even more significant: the presence of sodium and potassium salts in the ice particles being ejected from Enceladus. These salts are exactly what you would expect to find if liquid water had been in prolonged contact with rock, dissolving minerals over time and becoming salty in the process, much as Earth's oceans have become salty through eons of interaction with the continental crust. The concentrations and ratios of sodium and potassium in the Enceladus particles were remarkably similar to those found in Earth's own seas, suggesting that the plumes were not simply the sublimation of surface ice, but were instead sampling a body of liquid water that had existed long enough to acquire a significant mineral content. This was powerful evidence for a subsurface ocean, a hidden sea beneath the frozen exterior of this small moon. The question remained whether this ocean was merely a regional feature, perhaps a pocket of liquid water confined to the South Polar region near the Tiger Stripes, or whether it extended more broadly beneath the icy shell. The answer came in 2015, through an elegant application of orbital mechanics and careful observation. Scientists analyzed 7 years of imaging data to track the precise motion of Enceladus as it orbited Saturn, looking for a subtle wobble called libration that occurs as a moon's rotation responds to the varying gravitational pull of its parent planet. The amount of libration depends on the internal structure of the moon, on how mass is distributed and how different layers are coupled to one another, and the observations revealed that Enceladus wobbles more than it would if its icy shell were frozen solid to the rocky core below. The magnitude of the wobble indicated that the ice shell must be floating on a global layer of liquid water, that the ocean of Enceladus is not a local feature but extends beneath the entire surface, completely encircling the rocky interior of the moon. This global ocean exists beneath an ice shell that varies in thickness from perhaps 12 miles at the South Pole to roughly 18 miles at the equator, and the total volume of liquid water is estimated to be comparable to that of Earth's own oceans, despite Enceladus being so much smaller than our planet. The water is kept liquid by tidal heating, the same process that warms the interior of Jupiter's moon Io and drives its spectacular volcanic eruptions. As Enceladus moves through its slightly elliptical orbit around Saturn, it is alternately squeezed and stretched by the giant planet's gravity, and this continuous flexing generates friction within the moon, producing heat that prevents the interior ocean from freezing solid. The heat is greatest at the South Pole, which explains why the tiger stripes and their associated plumes are concentrated there, and why that region shows signs of recent geological activity, while much of the rest of the surface appears older and more heavily cratered. The final major discovery came in 2017, just months before Cassini's mission would end, when analysis of data from the plume flybys revealed the presence of molecular hydrogen in the material being ejected from Enceladus. Hydrogen is a simple molecule, just two atoms bonded together, but its presence in the plumes carried profound implications for the possibility of life. On Earth, molecular hydrogen is produced in significant quantities at hydrothermal vents, those underwater hot springs where seawater seeps down through cracks in the ocean floor, becomes heated by proximity to magma, and then rises back up laden with dissolved minerals and gases. The chemical reactions that produce hydrogen at these vents also release energy that can be captured by microorganisms. And indeed, some of the most ancient forms of life on our planet are bacteria and archaea that derive their energy from the chemistry of hydrothermal systems. The detection of hydrogen in the plumes of Enceladus suggested that similar processes might be occurring on the seafloor of that distant moon, that hot water might be circulating through a rocky core and emerging into the ocean above, carrying both hydrogen and the potential for life. The combination of liquid water, organic compounds, mineral salts, and now evidence for hydrothermal activity created a picture of Enceladus as a world with all the basic ingredients that life as we understand it might require. Astrobiologist Chris McKee, who had spent decades studying the possibility of life beyond Earth, assessed that Enceladus had become the most promising place in the solar system to search for extraterrestrial life. This was not because life was certain to exist there, for we have no evidence that it does, but because Enceladus offered something unique among potentially habitable worlds, a way to sample the ocean without ever having to drill through the ice. The plumes continuously spray material from the subsurface sea into space, and a future spacecraft could fly through those plumes just as Cassini did, collecting samples and analyzing them for signs of biological activity. No other ocean world in the solar system offers such convenient access to its hidden waters. Over the course of its mission, Cassini performed 23 separate flybys of Enceladus, each one contributing to our growing understanding of this extraordinary moon. Some flybys focused on imaging, capturing detailed photographs of the surface and the plumes, while others prioritized the various spectrometers and particle detectors that could analyze the composition of ejected material. The trajectories were carefully planned to sample different parts of the plumes, to pass at different altitudes, and to observe the moon under varying illumination conditions. Each flyby built upon the knowledge gained from those before, and together they transformed Enceladus from an obscure icy satellite into one of the most intensively studied and scientifically significant worlds in the outer solar system. The story of Enceladus is in many ways the story of how exploration can overturn our assumptions and reveal wonders we never anticipated. No one expected to find active geology on such a small moon. No one predicted the existence of a global ocean beneath its icy surface, and no one imagined that hydrothermal vents might be operating on the seafloor of a world so far from the warmth of the sun. Yet Cassini found all of these things, and in doing so, it changed our understanding of where life might exist in the universe. The discoveries at Enceladus suggest that habitable environments may be far more common than we once believed, that even small icy moons in the cold outer reaches of planetary systems might harbor liquid water and the conditions necessary for life. This is a gentle revolution in our thinking, a quiet expansion of the possibilities for life beyond our home world. And it all began with a small anomaly in Saturn's magnetic field detected during a routine flyby in February of 2005. And now we come to perhaps the most beloved feature of the distant world we have been visiting together, those delicate luminous bands that have captivated observers since the earliest days of the telescope, the rings of Saturn, which Cassini was able to examine in such extraordinary detail over its many years of patient observation that we now understand them in ways that would have seemed impossible to earlier generations of astronomers. And what the spacecraft found there, drifting among those countless icy particles, was a system of such intricate complexity and surprising youth that it has fundamentally changed how we think about these beautiful structures that grace our solar system's second-largest world. When Galileo first turned his primitive telescope towards Saturn in the year 1610, he could not quite make sense of what he saw, describing the planet as having ears or perhaps being accompanied by two smaller bodies pressed against its sides. And it was not until Cassini-Huygens observed Saturn with a better instrument in 1655 that the true nature of these features became clear, revealing them to be a flat ring surrounding the planet but nowhere touching it. And in the centuries that followed, astronomers gradually discerned more structure within what had appeared to be a single band, identifying gaps and divisions and multiple distinct rings. Yet even the most powerful Earth-based telescopes could only hint at the true complexity waiting to be discovered by spacecraft that could venture close enough to see the rings in all their intricate glory. The Cassini orbiter, with its suite of instruments designed specifically to study ring systems, revealed that what appears from Earth as perhaps a handful of distinct rings is in fact composed of more than 10,000 individual ringlets, each one a concentration of countless particles of ice and rock and dust, orbiting Saturn in stately procession according to the same gravitational laws that govern the motion of planets around the Sun. And this number, 10,000 distinct ringlets, gives some sense of the extraordinary complexity that awaited the patient instruments aboard the spacecraft. Structures within structures within structures. A nested hierarchy of gravitational and collisional dynamics playing out across a disk spanning some 280,000 kilometers from inner edge to outer boundary, yet in most places no thicker than the height of a modest house. Among the most intriguing discoveries made possible by Cassini's close examination of the rings were the curious features that scientists came to call propellers. Disturbances in the ring material caused by moonlets too small to clear complete gaps but large enough to create distinctive patterns in their wake, shaped rather like the propeller of an aeroplane when viewed from above, with regions of enhanced and depleted particle density extending outward from the central embedded object. And these propellers ranged in size considerably, with the largest ones earning individual nicknames from the scientists who studied them most closely. The grandest of these features being named Blériot after the French aviator Louis Blériot, who made the first flight across the English Channel in 1909, a fitting name for a structure created by an object perhaps a kilometer across, itself too small to see directly but making its presence known through the elegant disturbance it creates in the surrounding ring material as it pursues its endless orbit around the planet. The year 2009 brought a rare celestial alignment that offered Cassini an unprecedented opportunity to observe features in the rings that are normally invisible. For at that time Saturn reached its equinox, the moment when sunlight falls directly upon the planet's equator, and the rings, which lie in the equatorial plane, are illuminated edge-on by the sun, casting any vertical structures into sharp relief through the long shadows they project across the normally flat expanse of icy particles. And what the spacecraft observed during this fleeting window of special illumination was quite remarkable indeed, revealing structures in the B ring, the brightest and most opaque of Saturn's main rings, that rose to heights of approximately 2.5 miles above the ring plane, or roughly 4 kilometers, towering spires and ridges of ring material that had been disturbed from its usual flat configuration by gravitational interactions that scientists are still working to fully understand. These vertical structures, visible only through the shadows they cast during the equinox geometry, demonstrated that the rings are not always the perfectly flat disk they appear to be when viewed under normal illumination, but rather a dynamic system subject to waves and distortions and localized disturbances that can pile material into temporary towers of considerable height, relative to the usual thickness of the rings. And the images of these shadowy features, stretching across the ring plane like the shadows of mountain ranges at sunrise on Earth, provided scientists with entirely new perspectives on processes occurring within this vast orbiting disk of debris. The composition of the rings had long been a subject of scientific inquiry, with Earth-based spectroscopy suggesting they were made primarily of water ice, and Cassini's instruments confirmed and refined this understanding considerably, revealing that the rings are indeed composed almost entirely of water ice, remarkably pure in many regions, with only trace amounts of other materials mixed in, including various organic compounds that give certain parts of the rings a subtle reddish tinge. And the proportions of these contaminants vary from ring to ring and even within individual rings, providing clues about the origins and evolution of these structures that scientists continue to analyze with great interest. The water ice that makes up the bulk of the ring material ranges in particle size from tiny grains no larger than dust motes to chunks as big as houses, and even some objects several kilometers across, though the vast majority of the ring mass is contained in particles of modest size, somewhere between a snowball and a small automobile. endlessly colliding and jostling and accreting and fragmenting as they pursue their orbits around Saturn at speeds of tens of thousands of kilometers per hour, yet moving so nearly in parallel with their neighbors that collisions occur at relative velocities of only a few meters per second, gentle enough that the particles generally stick together or bounce apart without shattering into ever smaller fragments. Perhaps the most surprising discovery to emerge from Cassini's long investigation of the rings came during the final phase of the mission, the grand finale, when the spacecraft flew repeatedly through the gap between the innermost ring and the planet's cloud tops, allowing precise measurements of the gravitational influence exerted by the ring mass on the spacecraft's trajectory. And from these careful measurements, scientists were able to determine the total mass of the rings with unprecedented accuracy, finding it to be roughly 15 million trillion kilograms, which may sound impressive but is in fact only about 40% of the mass of Saturn's moon Mimas, one of the smaller mid-sized moons of the Saturnian system. This relatively modest mass, measured with such precision during the grand finale, led to a conclusion that many scientists found quite surprising and some found rather controversial, for it suggested that the rings are not ancient structures dating from the formation of the solar system some 4.5 billion years ago, as had long been assumed, but rather comparatively recent additions to the Saturnian system, perhaps only 10 to 100 million years old, a mere fraction of the age of the planets themselves, which would mean that if we could travel back in time to visit Saturn during the age of the dinosaurs on Earth, we might find the planet without its magnificent rings, or at least with rings far less substantial than those we observe today. This conclusion follows from the observation that the rings are remarkably bright and clean, composed of nearly pure water ice with relatively little contamination from the dark rocky and organic material that constantly drifts through the outer solar system in the form of micrometeoroids and dust from comets. And if the rings were truly ancient, 4.5 billion years of accumulating this cosmic debris should have darkened them considerably, like snow beside a road gradually becoming grey and dingy with accumulated grime. Yet the rings remain bright and white and largely pristine, suggesting either that they are young or that some process constantly renews their surfaces, and the mass measurement from the grand finale supports the youth hypothesis, for a more massive ring system could better resist contamination over long periods. If the rings are indeed young in geological terms, then the question naturally arises of where they came from, and scientists have proposed several possibilities, including the catastrophic disruption of a moon perhaps the size of Mimas by the impact of a large comet, or the tidal destruction of a moon that wandered too close to Saturn and was torn apart by gravitational forces, or the collision of two existing moons that reduced both to the rubble we now see spread across the equatorial plane. And while the precise origin remains uncertain, the evidence strongly suggests that the rings we admire today may be a transient feature of the Saturnian system, beautiful and intricate but not permanent on the timescales of planetary evolution. The transient nature of the rings is underscored by another discovery from Cassini's observations, the phenomenon that scientists have come to call ring rain, in which material from the innermost portions of the ring system spirals gradually inward and falls into Saturn's atmosphere, drawn downward by the planet's gravitational field and guided by magnetic field lines in a process that removes roughly 10,000 kilograms of ring material every second, a rate that may sound modest but which accumulates over millions of years into a substantial loss of mass from the rings, contributing to their eventual dissipation if no new material is added to replace what is lost. This rain of ring particles into Saturn's atmosphere was detected through observations of the planet's upper atmosphere and ionosphere, where the influx of water and organic compounds from the rings produces measurable changes in chemistry and electrical conductivity. And the discovery of this ongoing process helped confirm that the rings are not in equilibrium but rather slowly evolving. gradually losing mass to the planet below while perhaps also slowly spreading outward due to collisions among the particles. A system in dynamic transformation even if the changes occur too gradually for human eyes to perceive over the span of a single lifetime. Among the structural features revealed by Cassini's long investigation is the remarkably sharp outer edge of the A ring, the outermost of Saturn's main bright rings, which terminates not in a gradual fading away but in a crisp boundary maintained by the gravitational influence of the small moon Janus, which shares its orbit with the even smaller moon Epimetheus in a curious gravitational dance that we may discuss another time. And this relationship between ring edge and moon orbit illustrates how the moons and rings of Saturn interact in complex ways, with moons herding ring particles, opening gaps, creating waves, and generally sculpting the ring system into the elaborate structure we observe today. The year 2009 also brought the announcement of an entirely new ring around Saturn, discovered not by Cassini's cameras but by the Spitzer Space Telescope observing in infrared wavelengths from its orbit around the Sun. A ring so diffuse and composed of such dark material that it had escaped detection until instruments sensitive to the faint thermal glow of cool dust were trained upon the Saturnian system. And this ring, associated with the distant moon Phoebe and therefore called the Phoebe ring, proved to be truly enormous in scale, extending from roughly 6 million to about 18 million kilometers from Saturn, with a thickness of some 2.5 million kilometers, dwarfing the main ring system in sheer spatial extent, though containing far less material spread across this vast volume. The Phoebe ring is tilted some 27 degrees to the plane of the main rings, matching the inclined orbit of its namesake moon, which travels around Saturn in the opposite direction to most of the planet's other moons, and is thought to be a captured object from the outer solar system rather than a body that formed in place. And the ring is thought to consist of dark dust knocked loose from Phoebe's surface by micrometeoroid impacts, gradually spiraling inward towards Saturn and in the process darkening one hemisphere of the moon Iapetus, solving a mystery about that world's striking two-toned appearance that had puzzled astronomers for centuries. And so we see that the rings of Saturn, those most iconic features of our solar system's most beautiful planet, are neither simple nor static nor perhaps even ancient, but rather complex dynamic structures of surprising youth and ongoing evolution, revealed in all their intricate glory by a spacecraft that spent more than a decade drifting among them, photographing and measuring and discovering with the patient thoroughness that characterizes the best of human scientific endeavor. And though much remains to be understood about these elegant bands of orbiting ice, we now know them far better than we did before Cassini began its long journey through the Saturnian system. Knowledge that can accompany us as we drift peacefully towards sleep, perhaps dreaming of endless particles of ice catching the distant sunlight as they circle forever around their giant world. Saturn, as we have come to understand through the long and patient observations of Cassini, is not merely a planet adorned with rings, but rather the center of its own miniature solar system, a gathering place for more than 80 moons that range from tiny irregular fragments no larger than a modest hill to great spherical worlds with their own complex geologies and atmospheres. Each of these moons carries its own quiet story, shaped over billions of years by the gentle but persistent forces of gravity, tidal heating, and the slow accumulation or erosion of surface materials. And together they form what one might reasonably describe as a menagerie, a collection of forms so varied and unexpected that even the most imaginative planetary scientists found themselves surprised again and again as Cassini sent back its detailed observations across the vast distance to Earth. Among the most visually striking of Saturn's moons is Iapetus, a world that has puzzled astronomers since Giovanni Cassini himself first observed it in the 17th century, and noted something peculiar about its brightness, how it seemed to vanish and reappear as it orbited the planet, as though one half of its surface were made of coal and the other of fresh snow. The spacecraft that bore his name finally revealed the full truth of this two-toned world in December of 2004, when Cassini made its first close approach and captured images that showed the dramatic contrast in stunning clarity. The leading hemisphere, the side that faces forward as Iapetus moves along its orbit, is coated in a dark reddish-brown material so dark that it reflects only about 4% of the light that falls upon it, while the trailing hemisphere gleams with ice so bright it reflects perhaps 50% of incoming sunlight, creating a difference so stark that the Moon appears almost to be two separate bodies somehow joined together. The explanation for this remarkable dichotomy, as scientists gradually piece together from Cassini's observations, involves a delicate interplay of external dust and thermal processes that together have amplified what may have begun as a subtle difference into the dramatic two-toned appearance we see today. Dark material, possibly originating from the outer irregular moons that orbit Saturn in retrograde directions and slowly spiral inward as micrometeorites knock particles loose from their surfaces, drifts inward and settles preferentially on the leading hemisphere of Iapetus. Once deposited, this darker material absorbs more sunlight and warms slightly, causing the ice beneath and around it to sublimate, to transform directly from solid to vapor and drift away toward the colder trailing hemisphere where it refreezes as fresh bright ice. This thermal segregation process, operating over millions upon millions of years, has effectively painted Iapetus in two colors: dark where the dust accumulated and bright where the ice migrated and settled. But the coloration of Iapetus, striking as it is, proved not to be the most surprising feature Cassini would reveal about this moon. Running along the equator, like a belt cinched around the middle of the world, rises a mountainous ridge of such improbable height that scientists struggled at first to explain how it could possibly exist. This equatorial ridge, stretching for more than 1,600 kilometers along the Moon's midsection, reaches heights of up to 20 kilometers in places, which is to say roughly 12 miles, a figure that becomes truly remarkable when one considers that Iapetus itself is only about 1,470 kilometers in diameter. Relative to the size of the body upon which it stands, this ridge represents the tallest known mountain range in our solar system, dwarfing even the mighty Olympus Mons on Mars when the comparison accounts for the respective sizes of the worlds. How such a feature came to exist remains a question that planetary scientists continue to discuss with quiet interest, proposing various possibilities that include the freezing of a subsurface ocean that caused the Moon to expand and crack along the equator, or the collapse of a ring system that once encircled Iapetus itself in the distant past, with the ring material gradually falling onto the equator and piling up into this imposing ridge. Whatever its origin, the ridge gives Iapetus an appearance somewhat like a walnut, a comparison that has been made by more than a few observers, and it stands as a reminder that even worlds we thought we understood from telescopic observations could hold features entirely beyond our expectation, waiting patiently to be discovered by spacecraft willing to make the long journey. Moving inward through Saturn's system of moons, we encounter Hyperion, a body so unlike the smooth spherical moons we typically imagine that it seems almost to belong to a different category of celestial object altogether. Hyperion is the largest known irregular moon in the solar system, measuring roughly 360 kilometers along its longest axis, and its shape can perhaps best be described as something like a potato, though even this comparison fails to capture the truly strange texture of its surface. When Cassini flew past Hyperion in September of 2005 and trained its cameras upon this tumbling world, the images revealed a surface pocked with deep, sharp-edged craters so closely packed and so uniformly dark at their bases that the Moon resembles nothing so much as a natural sponge, the kind one might find washed up on a beach. All holes, and cavities with thin walls between them. The explanation for this sponge-like appearance involves the unusually low density of Hyperion, which suggests that the Moon is highly porous, perhaps composed of water ice riddled with empty spaces like a frozen honeycomb. When meteorites strike such a surface, instead of excavating material and tossing it outward in the familiar pattern of crater formation, they tend to compress the porous ice and punch deep, narrow holes, preserving the sharp edges and creating the cellular texture that Cassini observed. The dark material at the bottom of these craters appears to be similar to the dark material found on Iapetus, adding to the evidence that such material drifts through the Saturnian system and settles on various moons according to their positions and surface conditions. Adding to the peculiarity of Hyperion is its rotation, which cannot be described as spinning in any orderly fashion but rather tumbles chaotically as it orbits Saturn, never presenting the same face toward the planet from one orbit to the next. This chaotic rotation results from the irregular shape of the Moon combined with the gravitational influences it experiences, and it means that predicting exactly how Hyperion will be oriented at any future time is essentially impossible beyond a certain horizon. A lovely example of deterministic chaos operating on an astronomical scale, where the fundamental laws of physics are perfectly well understood but the complexity of the system prevents long-term prediction nonetheless. Closer still to Saturn we find Mimas, a moon just under 400 kilometers in diameter that achieved a certain cultural fame when Cassini's images revealed how strongly it resembles a fictional space station from popular cinema. The feature responsible for this resemblance is the Herschel crater, a vast impact basin roughly 130 kilometers across, which is to say approximately 80 miles, spanning fully one-third of the Moon's entire diameter. If an impact of proportionally similar size had struck the Earth, the resulting crater would have stretched from London to Moscow, a scale of devastation almost beyond imagining. The impact that created Herschel must have come very close to shattering Mimas entirely, and indeed fractures on the opposite side of the Moon suggest that shock waves from the collision propagated through the body and nearly tore it apart. Within the Herschel crater rises a central peak some 6 kilometers tall, formed when the floor of the crater rebounded upward immediately after the impact, and the walls of the crater descend roughly 5 kilometers below the surrounding terrain, creating a feature that dominates the geography of this small icy world. The crater was named after William Herschel, the astronomer who discovered Mimas in 1789, and it serves as a permanent record of the violent processes that have shaped the moons of the outer solar system, where impacts of tremendous energy were once common and have left their marks upon nearly every surface we have examined. Beyond these individual worlds, Cassini revealed the quiet elegance of certain moons that share their orbits with others in stable gravitational arrangements that can persist for billions of years. The Trojan moons, as they are called, occupy positions 60 degrees ahead of or behind a larger moon in the same orbit, stationed at the stable Lagrange points where the gravitational influences of Saturn and the larger moon balance in such a way that small bodies can remain indefinitely without drifting away. Tessis, a mid-sized icy moon some 1,060 kilometers across, is accompanied by two such Trojans, the small irregularly shaped moons named Telesto and Calypso, which lead and trail Tessis respectively in its orbit around Saturn, like modest attendants accompanying a more prominent figure on an endless circular journey around the ringed planet. Among the smaller moons, Cassini revealed forms shaped not by ancient impacts but by the gentle ongoing accumulation of material from Saturn's rings. Atlas, a tiny moon only about 30 kilometers across, was found to possess a remarkably flat equatorial ridge that gives it the appearance of a flying saucer, a shape that results from ring particles gradually settling onto its equator over millions of years. Because Atlas orbits just outside the edge of the main ring system, it sweeps up particles that drift outward, and these particles, approaching the Moon with very low relative velocities, settle gently onto the surface rather than excavating craters, building up the distinctive ridge that Cassini photographed in such detail during its extended mission. The moon Dione, orbiting Saturn at a distance of roughly 377,000 kilometers, presented its own geological puzzles when Cassini examined its surface and revealed the true nature of features that had appeared in earlier, less detailed images as mysterious wispy markings. These wisps, it turned out, are not deposits of frost or volcanic material as some had speculated, but rather vast systems of ice cliffs, bright fractures in the moon's crust where relatively fresh ice has been exposed along the cliff faces. The tectonic forces that created these cliffs may be related to the orbital resonance that Dione shares with Enceladus, a 2-to-1 relationship in which Enceladus completes exactly 2 orbits for every 1 orbit of Dione, a gravitational dance that gently flexes both moons and may contribute to the geological activity observed on each. Speaking of orbital resonances, these elegant mathematical relationships thread throughout the Saturnian system, connecting moons to one another and moons to rings in ways that shape the entire architecture of this miniature solar system. Mimas, despite its small size, exerts a gravitational influence that clears a gap in Saturn's rings known as the Cassini division, the dark band between the A and B rings that is visible even in modest telescopes from Earth. Particles that would otherwise occupy this region are gradually nudged by Mimas into different orbits, their orbital periods falling into resonance with the Moon and causing them to be pulled away until the gap stands relatively empty, a testament to the persistent cumulative power of gravitational interaction operating over astronomical timescales. In 2010, instruments aboard Cassini detected something unexpected around Rhea, Saturn's second-largest moon. A thin atmosphere, far too tenuous to be visible but measurable nonetheless, was found to contain oxygen and carbon dioxide, sustained by the interaction of Saturn's magnetic field with the icy surface of the Moon. Energetic particles trapped in Saturn's magnetosphere continually bombard the surface of Rhea, breaking apart water ice molecules and releasing oxygen atoms that briefly form an exosphere around the Moon before escaping into space, a process that continuously refreshes this faint envelope of gas. The discovery reminded us that even apparently dead and frozen worlds can harbor subtle processes that make them more dynamic than they might first appear. Throughout the mission, Cassini also discovered 6 previously unknown moons orbiting Saturn, small bodies that had escaped detection from Earth but revealed themselves to the spacecraft's patient cameras. These discoveries brought the total count of Saturnian moons ever higher and suggested that still more small irregular bodies likely await discovery in the outer reaches of Saturn's gravitational influence, fragments and remnants from the early solar system captured or accreted over the billions of years since Saturn first formed. And so, as we rest here with this knowledge settling gently into mind, we can appreciate that Saturn's moons are not merely a collection of icy spheres orbiting a planet, but rather a diverse assembly of worlds, each with its own character, from the two-toned mystery of Iapetus with its impossible ridge, to the spongy tumbling chaos of Hyperion, to the impact-scarred face of Mimas, to the delicate orbital ballets of the Trojans and the resonant pairs, each one a quiet chapter in the longer story of how our solar system came to be and how it continues, even now, to slowly evolve. Saturn itself, the great ringed world that gave this mission its purpose, proved to be as mysterious and as rewarding as any of the moons that circle it. And over the course of 13 years in orbit, Cassini turned its instruments again and again toward the planet's butterscotch atmosphere, toward the banded clouds and the swirling storms, toward the poles where strange geometries persist and where lights dance in colors that no human eye has ever seen directly. And what the spacecraft found there, in the depths and heights of that immense gas giant, challenged assumptions that had stood for decades and revealed secrets that planetary scientists are still working to understand. Even now, years after the mission ended and the spacecraft made its final passage into the clouds. Perhaps the most visually striking feature that Cassini observed was the hexagonal jet stream at Saturn's North Pole, a six-sided pattern of atmospheric flow that spans approximately 18,000 miles from one side to the other, which is to say that it is large enough to contain nearly 4 Earths placed side by side within its boundaries. And this hexagon is not a transient feature or a momentary arrangement of clouds, but rather a persistent and stable structure that has maintained its shape for decades, rotating with the planet and keeping its 6 corners sharp and distinct despite the constant motion of the atmosphere around it. The hexagon was first glimpsed by the Voyager spacecraft when they flew past Saturn in the early 1980s. But at that time, the North Pole was tilted away from the Sun and shrouded in the long darkness of Saturnian winter, which made detailed observation difficult, and so the feature remained somewhat mysterious, a curiosity noted in the data but not fully explored. When Cassini arrived at Saturn in 2004, the North Pole was still experiencing winter conditions, and the hexagon was hidden in shadow. But as the years passed and Saturn moved along its slow orbit, the northern hemisphere gradually tilted toward the Sun, and by 2009, Cassini was able to observe the hexagon in visible light for the first time since the Voyager encounters, confirming that the pattern had persisted across all those intervening years, that it had continued to rotate and to maintain its distinctive shape through the long Saturnian seasons, each of which lasts more than 7 Earth years. The hexagon rotates approximately once every 10 hours and 39 minutes, which appears to be closely tied to the rotation of Saturn's deep interior. And within the hexagon, at the very center of the pole, sits a smaller vortex that swirls like a hurricane on Earth but with winds that reach speeds of over 300 miles per hour. The cause of the hexagonal shape has been the subject of considerable study and some debate, and the most widely accepted explanation involves the interaction between the polar vortex at the center and the surrounding jet stream, where differences in wind speed create standing wave patterns that become locked into a 6-sided configuration, and laboratory experiments using rotating fluids have managed to reproduce similar polygonal shapes under certain conditions, suggesting that the hexagon emerges naturally from the physics of rotating atmospheres rather than from any unique property of Saturn itself. It is, in its way, a demonstration of how fluid dynamics can produce unexpectedly orderly patterns from what might seem like chaotic conditions, and there is something quietly beautiful about that. About the idea that deep mathematical regularities can emerge from the turbulent flow of gases in the upper atmosphere of a distant world. Beyond the hexagon, Cassini observed many other atmospheric phenomena, including a spectacular storm that erupted in late 2010 and continued into 2011, a disturbance so large and so bright that it became visible through modest telescopes on Earth, appearing as a white spot against the yellowish bands of Saturn's atmosphere. This storm, known as the Great White Spot or sometimes as the Great Northern Storm, was the largest observed on Saturn since 1990, and it grew rapidly after its initial detection, stretching around the planet until its head caught up with its own tail, creating a band of disturbed atmosphere that encircled the entire globe. The storm churned ammonia ice and other materials up from the deeper layers of the atmosphere, bringing them to altitudes where they could be detected by Cassini's instruments, and the energy released by the storm was equivalent to many times the total energy output of all human civilization, a reminder of the scales involved when dealing with giant planets. These great storms appear to occur on Saturn roughly once every 30 years, which corresponds approximately to one Saturnian year, and they tend to appear in the northern hemisphere during the summer season, suggesting that their occurrence is somehow linked to the seasonal cycle of solar heating, though the precise mechanism remains uncertain. The 2010 storm was particularly valuable for scientific study because Cassini was present to observe it from orbit, gathering data that could not have been obtained from Earth-based telescopes or from brief flyby missions. And this data revealed that the storm had stirred up materials from depths of at least 100 miles below the visible cloud tops, providing a rare glimpse into the composition of Saturn's deeper atmosphere. One of the fundamental questions about Saturn that Cassini sought to address was the nature of its internal heat source, and measurements confirmed that Saturn radiates approximately 2.5 times more energy than it receives from the Sun, which means that there must be some internal process generating heat within the planet's interior. This excess heat is thought to come primarily from two sources, the first being the slow gravitational contraction of the planet over billions of years, as Saturn gradually shrinks and converts gravitational potential energy into thermal energy, and the second being the process known as helium rain, in which helium, which is slightly denser than hydrogen, slowly separates from the hydrogen in Saturn's upper layers and sinks toward the core, releasing energy as it falls. The measurement of this energy balance and the detailed observations of how heat flows through Saturn's atmosphere provided constraints on models of the planet's interior structure and helped scientists understand how giant planets evolve over the lifetime of a solar system. Among the many images that Cassini returned during its mission, one has achieved particular fame for its perspective on our own world, and that is the natural color image captured on the 19th of July, 2013, showing Saturn and its rings illuminated from behind by the Sun, with a tiny pale blue dot visible just below and to the right of the rings, and that dot, easily overlooked among the billions of ice particles that make up the rings themselves, was Earth. This image, sometimes called the day the Earth smiled, was notable not only for its scientific value but also for the way it was obtained, with the imaging team announcing in advance that Cassini would be photographing Earth and inviting people around the world to step outside and wave at Saturn at the appointed time, a gesture that was of course far too small to be detected by any instrument, but which served as a reminder of the connection between the distant spacecraft and the people who had built it and who followed its journey. The question of how fast Saturn rotates, which might seem like a straightforward measurement, turned out to be surprisingly complicated, and Cassini's observations contributed to what became known as the Saturn day-length controversy. When the Voyager spacecraft flew past Saturn in 1980 and 1981, they measured the rotation period by tracking periodic variations in radio emissions that were linked to the planet's magnetic field, and this gave a value of approximately 10 hours 39 minutes and 24 seconds, which was adopted as the official rotation period for many years. However, when Cassini began making similar measurements in the 2000s, it found that the radio period had changed, appearing to be several minutes longer than the Voyager value, which was puzzling because a planet's rotation period should not change significantly over such a short time. The resolution to this puzzle came from the realization that the radio emissions are not directly tied to the rotation of the planet's deep interior, but rather are influenced by the interaction between Saturn's magnetic field and the charged particles in its magnetosphere. And these interactions can be affected by the solar wind and by other factors that vary over time. Cassini scientists eventually developed alternative methods for estimating the rotation period, including measurements of the planet's gravitational field and observations of atmospheric waves, and these suggested a true rotation period closer to 10 hours 33 minutes, though some uncertainty remains. The difficulty of measuring something as fundamental as how fast a planet spins illustrates the challenges inherent in planetary science, where even apparently simple questions can have complicated answers. Another surprise came from measurements of Saturn's magnetic field, particularly observations made during the grand finale orbits in 2017, when Cassini passed between the planet and its rings and came closer to Saturn's cloud tops than ever before. These measurements revealed that Saturn's magnetic field is remarkably symmetric, with a tilt of less than 0.06 degrees between the magnetic axis and the rotational axis, which is essentially zero within the precision of the measurements. This near-perfect alignment is puzzling because theories of planetary dynamos, the processes by which rotating fluid interiors generate magnetic fields, generally predict that some degree of tilt is necessary for the dynamo to function, and the magnetic fields of Earth, Jupiter, Uranus, and Neptune all show significant tilts between their magnetic and rotational axes. The discovery of Saturn's nearly perfectly aligned magnetic field has prompted planetary scientists to reconsider their understanding of dynamo theory, and several possible explanations have been proposed, including the possibility that Saturn's magnetic field is generated by a different mechanism than other planets, or that some feature of Saturn's internal structure hides the true asymmetry of the field from external observation. One suggestion is that a layer of helium rain, falling through the atmosphere at a certain depth, might act to stabilize the outer part of the field and filter out the asymmetric components, leaving only the symmetric portion visible to spacecraft like Cassini, but this remains a topic of ongoing research. At both of Saturn's poles, Cassini observed aurorae, the glowing displays of light that occur when charged particles from the solar wind or from the planet's own magnetosphere interact with the upper atmosphere and cause atmospheric gases to emit light. Saturn's aurorae are similar in some ways to the northern and southern lights on Earth, but they are much larger and more powerful, and they glow primarily in ultraviolet wavelengths that are invisible to the human eye, though Cassini's instruments were able to capture them in detail. The aurorae were observed to vary in intensity and shape over time, responding to changes in the solar wind and to processes within Saturn's magnetosphere, and they provided valuable information about the complex electromagnetic environment that surrounds the planet. During the grand finale, Cassini also made detailed measurements of the composition of Saturn's deep atmosphere, using its mass spectrometer to sample the gases directly and using other instruments to probe the atmosphere remotely. Among the discoveries was an unexpected pattern in the distribution of ammonia, with the concentration varying with latitude in ways that suggested complex circulation patterns in the deep atmosphere, with ammonia being transported downward in some regions and upward in others. These observations complemented the data from the 2010 storm and from other atmospheric studies, building up a more complete picture of how Saturn's atmosphere is structured and how it moves, layer by layer, from the cloud tops down to the hidden depths where pressure and temperature increase steadily toward the planet's core. All of these observations, from the hexagon to the storms to the magnetic field measurements, represented pieces of a larger puzzle, each one adding something to our understanding of what Saturn is and how it works, and together they confirmed that even after decades of study, even after flybys by Pioneer and Voyager and 13 years of orbital exploration by Cassini, Saturn still held secrets that would take years to fully interpret. The data gathered by Cassini will continue to be analyzed for many years to come, and it will inform the design and planning of future missions, ensuring that the knowledge gained from those 20 years of observation will not be forgotten but will instead serve as the foundation for the next generation of discoveries about the Great Ring Planet and its place in our solar system. The grand finale phase of the Cassini mission began on the 22nd of April, 2017, marking the commencement of what would become one of the most ambitious orbital maneuvers ever attempted in planetary exploration. A series of 22 carefully planned orbits that would thread the spacecraft through a region of space no human-made object had ever visited. The narrow gap between Saturn and its innermost visible ring. A corridor approximately 1,500 miles wide that had remained utterly unknown until Cassini dared to pass through it. And this final chapter of the mission would yield scientific treasures that the original mission planners could scarcely have imagined when they first conceived of the spacecraft decades earlier. The decision to send Cassini through this gap was not made lightly, and represented years of careful deliberation among the mission team, who understood that this region of space might contain debris or dust particles dense enough to damage or destroy the spacecraft on its very first passage. And yet the scientific rewards of passing so close to both the planet and the inner edge of the rings were simply too valuable to forego, offering the chance to make measurements of Saturn's gravitational field with unprecedented precision, to sample ring particles directly, and to analyze the composition of Saturn's upper atmosphere in ways that could only be accomplished by flying through that tenuous outer layer of gas. On that April day when the grand finale began, Cassini performed its final close flyby of Titan, the 127th encounter with that hazy orange moon over the course of the mission. And this particular passage was designed with a very specific purpose in mind: to use Titan's substantial gravity to bend Cassini's trajectory and set the spacecraft on its new course, an orbital path that would repeatedly carry it between the planet and the rings. And the navigation team referred to this final Titan encounter as the goodbye kiss, a gentle phrase that captured both the affection they felt for this mission they had tended for so many years and the bittersweet nature of this last gravitational assist, which would ultimately lead to the spacecraft's end. The geometry of this gravitational maneuver was elegant in its precision, with Titan's pull altering Cassini's velocity by just the right amount to reshape its orbit around Saturn, lowering the periapsis, which is the closest point to the planet in each orbit, from outside the rings to within that narrow gap. And once this trajectory change was accomplished, there would be no going back. The spacecraft was committed to its new path, and each subsequent orbit would carry it through that unexplored region between cloud tops and ring edge, closer to Saturn than any spacecraft had ever ventured. 4 days after the Titan flyby, on the 26th of April, 2017, Cassini executed its first dive through the ring planet gap, passing through at a velocity of approximately 77,000 miles per hour. A speed so great that even a tiny grain of ring material could potentially cause significant damage to the spacecraft's instruments or systems. And as Cassini approached this, crossing the mission team oriented the spacecraft so that its large high-gain antenna dish faced forward, serving as a protective shield against any particles the spacecraft might encounter, a configuration that meant Cassini could not communicate with Earth during the crossing itself. The wait that followed was an exercise in patience for the mission team, who knew they would have no contact with their spacecraft for approximately 20 hours, a long stretch of silence during which Cassini would make its crossing, continue around its orbit, and finally reorient itself to point its antenna back toward Earth. And during those quiet hours, the scientists and engineers could only wait and hope that the gap had proven as benign as their best models suggested, that the spacecraft they had guided for so long had survived this first passage through unknown territory. When the signal finally arrived, strong and clear, it confirmed that Cassini had passed through safely, and the data that began streaming back to Earth contained a wonderful surprise. For the gap between Saturn and its innermost ring proved to be remarkably clear of debris, far less dusty than many had feared, with the spacecraft's radio and plasma wave science instrument detecting only a handful of dust particle impacts during the crossing. far fewer than the hundreds of hits per second the instrument typically recorded when Cassini passed through the main ring plane at other locations. The project scientist Linda Spilker, who had devoted decades of her career to this mission, described how the team had identified this particular region as the safest spot for these daring passages, based on their best understanding of ring particle distribution and dynamics. And yet, even with this careful analysis, there had been genuine uncertainty about what Cassini would encounter. And the discovery that the gap was relatively dust-free came as a relief and a pleasant surprise, allowing the remaining 21 dives to proceed with somewhat greater confidence that the spacecraft would survive to complete its mission. Each of the 22 orbits during the grand finale carried Cassini to extraordinarily close approaches to Saturn's visible cloud tops, with the spacecraft passing as near as 1,012 miles above the uppermost layers of the planet's atmosphere, a distance that seems vast by human standards, but represents an almost unimaginably intimate encounter when one considers that Saturn itself spans more than 72,000 miles in diameter. And at these close approaches, Cassini's instruments could make measurements of the planet's gravitational field, magnetic field, and atmospheric composition with a precision that was simply impossible from greater distances. The gravity science measurements obtained during these close passes proved particularly valuable for understanding both the planet and its rings, as Cassini's radio link with Earth allowed scientists to track the spacecraft's motion with extreme precision, detecting tiny accelerations and decelerations caused by variations in Saturn's gravitational pull. And from these minute changes in velocity, the science team could map the distribution of mass both within the planet and in the ring system that surrounds it. One of the long-standing questions about Saturn's rings concerned their total mass, a quantity that had important implications for understanding both how the rings formed and how old they might be. And the grand finale measurements provided the most accurate determination of ring mass ever achieved, revealing that the total mass of the ring system is equivalent to approximately 40% of the mass of Saturn's moon Mimas, or roughly 100 million trillion kilograms, which is an enormous amount of material by human standards, but represents only a tiny fraction of the planet's own mass. This measurement of ring mass carried implications that surprised many scientists, as the relatively low mass suggested the rings might be considerably younger than Saturn itself, perhaps only 100 million years old or so, rather than having formed alongside the planet 4.5 billion years ago, though this interpretation remains a subject of ongoing discussion and research, with some scientists proposing alternative explanations that could allow for older rings. And as with many scientific questions, the matter is not entirely settled. The gravity measurements also revealed new information about Saturn's internal structure, the hidden layers beneath those famous cloud bands, where pressures and temperatures climb to extraordinary values and the familiar hydrogen and helium gas transforms into exotic states of matter. And by analyzing how Saturn's gravitational field varies with position, the scientists could construct models of how mass is distributed within the planet, leading to revised estimates of the depth at which hydrogen transitions from a molecular gas to a metallic liquid, a boundary that influences the planet's magnetic field and internal dynamics. During some of the later grand finale orbits, mission controllers commanded Cassini to dip even lower, actually skimming through the uppermost reaches of Saturn's atmosphere, and the spacecraft's ion and neutral mass spectrometer directly sampled molecules from this tenuous outer layer, tasting Saturn's atmosphere in a way that had never been possible before. And among the molecules detected were not only the expected hydrogen and helium, but also a surprising variety of more complex organic compounds, substances containing carbon and hydrogen arranged in ring structures and chains, which had apparently drifted down from the rings themselves or formed through chemical processes in the upper atmosphere. These complex organic molecules in Saturn's upper atmosphere represented an unexpected discovery, as scientists had not anticipated finding such elaborate chemistry occurring in this region, and the presence of these compounds raised new questions about the interactions between the rings and the planet, suggesting a constant rain of material from the rings into Saturn's atmosphere, a slow but steady transfer of mass that may contribute to the gradual evolution of both the rings and the planet over time. Another significant discovery from the grand finale measurements involved Saturn's rotation rate, which might seem like a straightforward quantity to determine but had in fact been surprisingly elusive, as Saturn's cloud patterns do not rotate uniformly and the planet lacks the obvious surface features that would make tracking rotation simple, and previous estimates based on different methods had yielded conflicting results, leaving scientists uncertain about exactly how fast the planet spins on its axis. The grand finale gravity measurements detected subtle internal oscillations within Saturn, waves propagating through the planet's interior that leave their imprint on the gravitational field. And by analyzing these oscillations, the science team was able to determine Saturn's rotation period with new precision, finding that the planet completes one rotation in approximately 10 hours, 33 minutes, and 38 seconds, a value that refined previous estimates and helped resolve the long-standing uncertainty about this fundamental property of the planet. As orbit followed orbit, each passage through the gap yielded its own collection of data, the spacecraft's instruments recording gravitational variations, magnetic field configurations, atmospheric compositions, and countless other measurements that would occupy scientists for years to come. And with each successful crossing, the mission team grew more confident that Cassini would complete its full sequence of 22 orbits, though they remained ever watchful for any signs of trouble, any unexpected effects from this prolonged operation in such an unusual orbital regime. The ring particles that Cassini's instruments detected during these passages were predominantly small, falling in the range of nanometers to micrometers in size, tiny motes of ice and dust that posed little threat to the spacecraft but provided valuable information about the composition and dynamics of the inner ring edge. And the data suggested that the gap is maintained by a combination of gravitational effects and electromagnetic interactions that sweep small particles either inward toward the planet or outward toward the rings, keeping this corridor relatively clear. Each grand finale orbit took approximately 6.5 days to complete, with the close approaches to Saturn occurring at intervals that allowed the mission team to process data, plan observations, and upload commands for the next passage, a rhythm of activity that continued through the Northern Hemisphere spring and into summer of 2017, as Cassini spiraled ever closer to its final destiny. The scientific return from these 22 orbits was extraordinary by any measure, representing a concentrated burst of discovery that complemented and extended the findings of the previous 13 years. And the data collected during this phase will continue to yield new insights for decades as researchers develop new analysis techniques and theoretical models that can extract additional meaning from the measurements Cassini so faithfully transmitted back to Earth. The geometric elegance of the grand finale trajectory reflected the accumulated wisdom of 2 decades of operations at Saturn, the mission team's intimate knowledge of the planet and its moons, allowing them to design a flight path that maximized scientific return while managing the very real risks of operating in this unexplored region. And the success of all 22 orbits stands as a testament to the skill and dedication of the engineers and scientists who guided Cassini through this final chapter of its long journey, the spacecraft performing beautifully even as it approached the end of its functional life, its instruments still sharp, its communication still clear, its orientation still precise, a mechanical explorer that had exceeded every expectation and was now preparing to make one final contribution to human knowledge of the ringed planet and its remarkable system of moons and rings that had been its home for so many years, a home it would soon enter forever in one last, deliberate plunge. On the morning of September 15th, 2017, In the darkness before dawn in California, a spacecraft that had traveled nearly 4 billion kilometers and had spent more than 13 years orbiting the ringed planet finally began its last ascent. Cassini had been awake and working through the quiet hours. Its instruments pointed toward Saturn, gathering measurements of the atmosphere that would soon consume it. The spacecraft was moving at approximately 113,000 kilometers per hour relative to Saturn, and its trajectory had been calculated with extraordinary precision by engineers who had spent months planning this final act. There would be no dramatic music playing in mission control, no countdown clock ticking toward zero, only the steady work of receiving data from a spacecraft that had become, over 2 decades, something like a trusted colleague to the thousands of people who had built it, launched it, guided it, and listened to its transmissions across the vast emptiness of space. The decision to end the mission in this particular way had been made years earlier, and it was rooted not in any failure of the spacecraft, but rather in a profound sense of responsibility toward worlds that Cassini itself had revealed to be far more interesting than anyone had imagined. When the mission launched in 1997, scientists knew that Saturn possessed a moon called Enceladus, a small icy body roughly 500 kilometers across, but they had little reason to suspect that this frozen world harbored anything remarkable beneath its surface. It was Cassini that changed everything, flying through the geysers that erupted from fractures near the moon's south pole and detecting water vapor and ice particles and, crucially, organic molecules and hydrogen gas. These discoveries suggested that Enceladus possessed a global ocean of liquid water beneath its icy shell, heated by tidal forces, and that this ocean might contain the chemical ingredients necessary for life. Similarly, Titan had revealed itself to be a world of extraordinary complexity, with lakes of liquid methane and a thick nitrogen atmosphere and organic chemistry occurring on a planetary scale. The spacecraft that had made these discoveries was powered by plutonium-238, and its fuel supply, while still adequate for operations, would eventually run low. Mission planners recognized that if Cassini was simply abandoned in orbit around Saturn, there was a chance, however small, that it might someday crash into Enceladus or Titan and contaminate those worlds with earthly microorganisms that might have survived the journey through space. The ethical response, they determined, was to deliberately destroy the spacecraft in a place where no life could possibly exist, the deep atmosphere of Saturn itself. And so the grand finale had been devised, a series of 22 orbits that carried Cassini between the innermost edge of Saturn's rings and the cloud tops of the planet, through a region where no spacecraft had ever traveled. Each of these passes brought new data about the mass and structure of the rings, the composition of Saturn's upper atmosphere, and the planet's internal magnetic field. The spacecraft performed beautifully throughout this final phase, its instruments working as intended, its attitude control systems keeping it properly oriented despite the thin wisps of atmospheric particles it encountered during its closest approaches. On September 11th, Cassini made one last distant pass by Titan, using the moon's gravity to bend its trajectory into a course that would intersect with Saturn's atmosphere 4 days later. This final Titan flyby was calculated to within a few meters of the planned altitude, a remarkable achievement given that the moon was more than 1 billion kilometers from the engineers who had designed the maneuver. The last image that Cassini captured was taken approximately 14 hours before the spacecraft entered Saturn's atmosphere. It showed a view of the planet's night side, with the location where Cassini would make its final entry visible as a darkened region lit faintly by ring shine. There was nothing dramatic about this image, no spectacular storms or intricate ring structures, simply a quiet view of the place where a long journey would end. The imaging science team had chosen to take this final picture knowing that there would be no opportunity for another, that the spacecraft's attention would soon turn entirely toward its atmospheric instruments and its radio antenna, which needed to remain pointed toward Earth to transmit the final measurements. In the hours before atmospheric entry, Cassini's thrusters fired periodically to keep the spacecraft oriented correctly, compensating for the tiny forces exerted by Saturn's gravity gradient and by the pressure of sunlight on its surfaces. The spacecraft was essentially falling toward Saturn, accelerating under the planet's immense gravitational pull, and its path had been refined by tracking data gathered over the preceding days. At the Jet Propulsion Laboratory in Pasadena, California, the mission operations team had gathered in the Spaceflight Operations Facility, the same room from which so many historic missions had been controlled. Earl Mays, who served as the Cassini program manager during these final years, stood among his colleagues as the final telemetry arrived. The spacecraft was transmitting in real time, sending data about the temperature and density and composition of Saturn's upper atmosphere as it descended, pushing its thrusters harder and harder to maintain its orientation against the increasingly dense atmospheric gases. At approximately 3:31 in the morning Pacific Daylight Time, which was 6:31 in the morning Eastern Daylight Time, the thrusters reached their maximum capacity. Saturn's atmosphere had grown thick enough that Cassini could no longer maintain its antenna pointed toward Earth, and the radio signal that had been arriving at the Deep Space Network's antennas in Canberra, Australia, simply stopped. There was no explosion, no dramatic final message, only the cessation of a signal that had been transmitting faithfully for 20 years. The light travel time from Saturn to Earth at that moment was approximately 83 minutes, which meant that by the time mission controllers received confirmation of signal loss, Cassini had already been gone for more than an hour. The spacecraft had become a meteor in Saturn's atmosphere, its components heating and fragmenting and ultimately vaporizing as it plunged deeper into the hydrogen and helium gases. Some engineers describe this as a spacecraft cremation, a gentle metaphor for the complete dispersal of Cassini's material into the very planet it had studied for so long. Nothing of the spacecraft would survive this descent. It would become, in a sense, a permanent part of Saturn itself. When Earl Mays announced the end of mission, the room was quiet. Some people embraced, others wiped tears from their eyes, and many simply stood in silence, contemplating the conclusion of something that had occupied a significant portion of their professional lives. There were no celebrations in the traditional sense, only a deep and complicated emotion that combined grief for the loss of a spacecraft with pride in what had been accomplished and gratitude for having been part of something so extraordinary. The mission had generated 453,048 images over the course of its time at Saturn, a number that seems almost impossible to comprehend. Each of these images had been captured by the spacecraft's camera systems, transmitted across more than 1 billion kilometers of space, received by antennas on Earth, processed by computers at JPL, and archived for scientists and the public to examine. The total volume of scientific data returned by Cassini amounted to approximately 635 gigabytes, which may seem modest by contemporary standards, but represented an enormous quantity of carefully gathered measurements about Saturn, its rings, and its moons. Over the course of its orbital mission, Cassini completed 294 orbits of Saturn, each one designed to accomplish specific scientific objectives. Some orbits carried the spacecraft close to Titan for gravity assists and atmospheric studies. Others brought it near the icy moons of the inner system, and still others were devoted to observing the rings at various angles and lighting conditions. The mission operations team executed approximately 2.5 million commands during the spacecraft's operational lifetime, each one carefully designed and tested before being uploaded to Cassini's onboard computer systems. The complexity of coordinating 13 years of orbital operations around a distant planet, with multiple instrument teams competing for limited resources and observation time, required extraordinary planning and cooperation among thousands of scientists and engineers. The scientific legacy of the Cassini mission continues to expand even now, years after the spacecraft's final plunge. As of the most recent counts, researchers have published more than 4,000 peer-reviewed scientific papers based on Cassini data, and this number continues to grow as scientists apply new analysis techniques to the archived observations. Graduate students who began their doctoral research using early Cassini data have since become professors training their own students, creating a generational chain of knowledge that extends far beyond the mission itself. Some scientists spent their entire careers working on Cassini, from the early planning stages in the 1980s through the launch in 1997 and the long cruise to Saturn, and finally the 13 years of orbital science. For these individuals, the end of the mission was not merely a professional milestone but something more personal, the conclusion of a relationship with a machine that had become central to their scientific identity. There were also younger scientists who grew up with Cassini, who remembered watching news coverage of the launch as children, and who later found themselves analyzing the very data that spacecraft was gathering. Some of these individuals have spoken about how Cassini shaped their decision to pursue careers in planetary science, how the images of Saturn's rings and the discoveries about Titan and Enceladus captured their imagination and never let go. The mission created a community that spanned generations and continents, bringing together researchers from 17 different nations to collaborate on the exploration of a world nearly 1.5 billion kilometers from Earth. The discoveries made by Cassini have inspired plans for future missions that will continue the exploration of the Saturn system. Most notably, NASA selected a mission called Dragonfly for development, a rotorcraft lander that will fly through the thick atmosphere of Titan, landing at multiple locations to study the Moon's surface chemistry and search for signs of prebiotic processes. Dragonfly is scheduled to launch in 2027 and will arrive at Titan in the mid-2030s, carrying instruments designed to build directly upon what Cassini revealed about this extraordinary world. The mission concept was made possible by Cassini's discoveries about Titan's atmospheric density and surface conditions, which demonstrated that a flying vehicle could operate in that environment. Scientists have also proposed missions to return to Enceladus, concepts with names like Enceladus Life Finder and Enceladus Orbolander, designed to fly through the plumes of water vapor erupting from the Moon's south pole and analyze the material for signs of biological activity. These proposals represent a direct response to Cassini's discovery that Enceladus possesses an ocean with apparent hydrothermal activity, making it one of the most promising places in the solar system to search for extraterrestrial life. While none of these Enceladus missions have yet been selected for development, they remain strong candidates for future exploration, and the scientific community continues to refine the instrument packages and mission designs that would make such investigations possible. The story of Cassini is, in many ways, a story about patience and persistence, about the long timescales over which scientific understanding accumulates. The mission was first conceived in the early 1980s, approved for development in the late 1980s, launched in 1997, arrived at Saturn in 2004, and operated until 2017. The full arc of the mission, from initial concept to final data analysis, spans more than 4 decades of human effort. Scientists who worked on Cassini proposals as young researchers retired before the mission ended, and students who analyzed Cassini data for their dissertations will likely still be working with that data when they themselves retire. This is the nature of planetary exploration, a multi-generational endeavor in which the accomplishments of one era provide the foundation for the questions of the next. And so the Cassini spacecraft, which had traveled so far and accomplished so much, came to rest in the atmosphere of Saturn, its material dispersed among the gases of the planet it had orbited for 13 years. The images and measurements it gathered remain accessible in archives around the world, available to any scientist who wishes to study them, and the discoveries it made continue to shape our understanding of the outer solar system. In the quiet hours of that September morning in 2017, a machine fell into Saturn's clouds and was gone, but what it taught us remains, patiently waiting to be rediscovered by each new generation of curious minds who turn their attention toward the distant worlds beyond our own.